Hello there, and welcome. I am so glad you found your way here tonight. Maybe it has been a long day, the kind that stretched on longer than it should have, the kind where your mind kept running, even when your body wanted to stop. That is perfectly all right. You do not have to carry any of that with you right now. Whatever is unfinished can wait until morning. Whatever is unresolved does not need to be solved tonight. You can set it all down now, gently, like setting a heavy coat on a chair by the door. You have nothing to do tonight but rest. Tonight, we are going to drift through the world of Jupiter, the largest planet in our solar system, a place so vast and so ancient and so quietly powerful that it has been shaping the story of our solar system since before the Earth itself existed. We will move slowly through its storms and moons and deep, swirling clouds, through the science of what it is and the wonder of what it means. There is no hurry. There is nowhere else to be. Let your breathing slow down now. Let your shoulders drop. Let the weight of your body sink into wherever you are lying. The room around you is quiet. The night is doing what the night does, holding everything still. If these calm journeys through the universe help you unwind and drift toward sleep, consider subscribing to the channel. We make these for you, one sleepy soul at a time. Now, let us begin. Jupiter is the largest object in the solar system that is not a star. It sits out there in the dark, beyond the rocky inner planets, beyond the asteroid belt, enormous and unhurried, a world so big that all the other planets combined could fit inside it with room left over. When you look at Jupiter through even a modest telescope, you can see its cloud bands, pale stripes of orange and cream and brown, wrapping around its middle like the rings of an old tree. It is a world made almost entirely of gas and liquid, with no solid surface to stand on, no ground beneath the clouds, just layers of atmosphere growing denser and hotter the deeper you go, until the hydrogen itself becomes something closer to a liquid metal than a gas. We have never touched the bottom of Jupiter. We may never know exactly what lies there, and there is something quietly right about that. The idea that some things are too deep, too vast, too ancient to be fully known. Something old and patient waits at the center of every vast, dark thing. Jupiter has been orbiting the Sun for over 4.5 billion years. It formed in the earliest days of the solar system, when the young Sun was still surrounded by a swirling disk of dust and gas, and gravity began pulling material together into clumps, then into rocks, then into worlds. Jupiter formed fast, faster than any other planet, sweeping up enormous quantities of hydrogen and helium before the solar wind blew the remaining gas away. By the time Earth was still a molten, cooling ball of rock, Jupiter was already ancient. It has seen every chapter of our solar system's history, drifting slowly in its orbit, circling the Sun once every 12 years, patient and enormous and impossibly old. It has been circling quietly since before the first stone on Earth had time to cool. Jupiter's great red spot is a storm that has been raging for at least 350 years. We have been watching it since astronomers first pointed telescopes at the sky in the 17th century, and it was already there, already spinning, already wide, already a feature of that distant world. At its largest, the Great Red Spot was once wider than 3 Earths placed side by side. It has been shrinking in recent decades, slowly, steadily, in a way that no one fully understands, but it is still there, still turning. A storm older than the United States, older than the Industrial Revolution, older than almost every human institution we consider ancient. The winds inside it move at hundreds of miles per hour, and yet from here, from Earth, it looks like a quiet oval of color, drifting in a slow and steady rotation, the way a leaf turns in a wide, still river. Even the wildest things, seen from far enough away, look slow and calm and restful. The 4 largest moons of Jupiter were discovered by Galileo in the year 1610. He turned his small, handmade telescope toward Jupiter one January night and noticed 4 tiny points of light that moved from night to night, shifting positions, circling the planet. He understood immediately what he was seeing. Other worlds, orbiting something other than Earth. It was one of the most consequential observations in the history of science. A quiet moment of watching that changed everything we thought we knew about our place in the universe. Those 4 moons, Io, Europa, Ganymede, and Callisto, are still there, still circling Jupiter, just as Galileo watched them do 400 years ago. Tonight, as you rest, those same moons are moving through their orbits in the dark. As you rest tonight, Galileo's 4 moons continue their ancient, unhurried orbits. Europa, one of Jupiter's moons, may contain a liquid water ocean beneath its icy surface. The surface of Europa is covered in a thick shell of ice, crisscrossed with long brown lines that look like cracks in a frozen pond. Beneath that ice, scientists believe there is a vast ocean of liquid water, kept liquid not by sunlight, which barely reaches that far from the sun, but by the heat generated as Jupiter's gravity squeezes and flexes the moon's interior, over and over, like kneading dough. The ocean may be deeper than any ocean on Earth. It sits in complete darkness, under kilometers of ice, warmed only by the slow grinding of tides. And in that dark, cold water, there may be life. We do not know. We have never been there. But the possibility sits quietly in the back of every planetary scientist's mind, that we are not alone, that something small and strange may be drifting through the darkness of Europa's deep, hidden sea right now. And somewhere in the dark, beneath the ice, something may be drifting without knowing it is being wondered about. Jupiter acts as a shield for the inner solar system. Because of its immense gravitational pull, Jupiter captures or deflects many of the comets and asteroids that would otherwise travel inward toward Earth. Over the billions of years of solar system history, Jupiter has absorbed countless impacts, drawing dangerous objects into itself, sending others out into the far reaches of the solar system, acting as a kind of silent protector for the small, fragile, rocky worlds closer to the Sun. Scientists believe that without Jupiter's gravitational influence, the inner solar system would be far more chaotic, with many more large impacts striking Earth at regular intervals. Life here, if it arose at all, might have had much less time to develop before being reset by a devastating collision. Jupiter does not know it is protecting us. It simply is what it is, vast and gravitationally powerful, doing what gravity does, quietly reshaping the paths of everything that passes near it. A quiet guardian does not need to know what it is guarding to do its work. Jupiter rotates faster than any other planet in the solar system. Despite being the largest planet, it completes one full rotation in just under 10 hours. A day on Jupiter, from one sunrise to the next, if you could somehow stand in its clouds and watch, would be shorter than a typical working day on Earth. This rapid rotation has consequences. It flattens the planet at the poles and bulges it at the equator, giving Jupiter a slightly squashed shape that is visible even in amateur telescopes. The fast spin also drives the powerful wind patterns we see in Jupiter's cloud bands, separating the atmosphere into distinct belts and zones that flow in opposite directions, creating the beautiful striped appearance that has made Jupiter one of the most recognizable objects in the night sky. Everything about Jupiter happens on a scale that is hard to hold in the mind, and yet, turning at that speed, it has the calm of something that has done the same thing billions of times before. Ancient things develop a kind of quiet confidence in their own rhythm. Jupiter's magnetic field is the strongest of any planet in the solar system. It is about 20,000 times stronger than Earth's magnetic field, and it extends so far into space that if you could see it, it would appear larger than the full moon in our night sky. This magnetic field traps charged particles from the Sun and from Jupiter's volcanic moon Io, creating intense radiation belts that surround the planet. The Galileo spacecraft, which orbited Jupiter for nearly 8 years, had to be carefully designed to withstand this radiation. Spacecraft passing through Jupiter's magnetic environment experience rapid instrument aging, like a kind of deep space weather that invisibly wears things down. The field itself is generated by the movement of liquid metallic hydrogen deep inside Jupiter, a substance that exists nowhere on Earth, a state of matter so exotic it can only form under the crushing pressures of a gas giant's interior, moving slowly in vast currents we cannot see. Even now, as you drift, invisible rivers of magnetism are flowing around a world we have barely touched. Io, the innermost of Jupiter's large moons, is the most volcanically active body in the solar system, not just more active than Earth, more active than anything else we have ever found. Io has hundreds of volcanoes, some of which eject sulfur plumes hundreds of kilometers into space. The surface of Io is constantly being resurfaced by lava, which means it has almost no impact craters, the normal scars of a solar system's long history of collisions. Instead, Io is yellow and orange and red and white, painted by different forms of sulfur at different temperatures. A world that looks almost alien, even by the standards of an already alien solar system. The energy driving all of this comes from Jupiter's gravity, which constantly flexes and pulls at Io, generating enormous amounts of internal heat. Io is being slowly torn apart and rebuilt, over and over, in a cycle that has been running for billions of years, in the cold dark beyond the asteroid belt. In the faint distance, a small world burns quietly, endlessly reshaping itself in the dark. Jupiter has at least 95 known moons, making it the planet with the most known moons in our solar system. Most of them are small and irregular, captured asteroids and chunks of rock that drifted too close to Jupiter's gravity well and never escaped. They orbit in all different directions, some moving in the same direction as Jupiter rotates, some moving in the opposite direction, some tilted at strange angles. The four Galilean moons, Io, Europa, Ganymede, and Callisto, are by far the largest, and they form a kind of miniature solar system of their own, with regular orbits and distinct personalities. But beyond them, dozens of smaller moons drift in elongated, eccentric orbits, some taking years to complete a single trip around Jupiter. They are mostly unnamed in the public imagination, small dark rocks circling quietly in the outer dark, known only by catalog numbers and the patient work of astronomers. The quiet ones, the unnamed ones, are still there, still circling, still patient, still part of the story. The Voyager spacecraft gave us our first close look at Jupiter in 1979. Voyager 1 and Voyager 2 flew past Jupiter within months of each other, sending back images and data that transformed our understanding of the Jovian system almost overnight. Before Voyager, we knew Jupiter was large and had storms and several moons. After Voyager, we knew about Io's volcanoes, about the thin rings of Jupiter, about the complexity of the cloud systems, about the way the Galilean moons each had their own unique character. The images Voyager sent back were, at the time, the most detailed ever taken of another planet. And then the spacecraft kept going, past Saturn, past Uranus, past Neptune, and eventually out of the solar system entirely, still traveling, still sending faint signals across the dark, still drifting away from us at tens of thousands of miles per hour, patient and irretrievable. Tonight, while you breathe slowly, Voyager continues its long, quiet journey into the dark between the stars. Jupiter has a ring system, though it is nothing like Saturn's. While Saturn's rings are bright and wide and made of ice, visible with a backyard telescope, Jupiter's rings are faint, thin, and dark. They are made mostly of tiny dust particles, shed from Jupiter's inner moons when they are struck by micrometeoroids. The rings were not discovered until Voyager 1 flew past in 1979, and even then, scientists had to look carefully to find them. They are invisible from Earth without specialized instruments. If you stood inside Jupiter's ring system and looked outward, you might not even realize you were in a ring at all. The particles are so sparse and so dark that the ring would appear more like a faint haze than a solid structure. Most of the rings in the outer solar system are like this: quiet, dark, easy to overlook, present only because someone looked carefully enough. Some of the most real things in the universe are the ones you have to look hardest to see. Ganymede is the largest moon in the solar system, larger than the planet Mercury. It is a world unto itself, with its own magnetic field, its own thin atmosphere, and a surface marked by ancient dark terrain and younger, grooved bright terrain that speaks to a complicated geological history. Ganymede orbits Jupiter at a comfortable distance, taking just over 7 days to complete one orbit, and it is thought to have a deep saltwater ocean beneath its icy surface, sandwiched between layers of ice. If Ganymede orbited the Sun instead of Jupiter, we would call it a planet without hesitation. But it circles Jupiter instead, one of 4 large moons, each one remarkable in its own way, each one carrying mysteries we have only begun to understand. Ganymede is a world in its own right, ancient and quiet, going about its slow orbit in the cold dark as it has done for billions of years. Quietly, the cosmos moves around you, and somewhere in that movement, a world larger than Mercury drifts in patient silence. Jupiter's atmosphere contains ammonia ice clouds that form the pale, cream-colored zones we see in photographs. The darker belts are regions where the atmosphere is descending, while the lighter zones are where it is rising. These belts and zones are driven by Jupiter's rapid rotation and by the planet's own internal heat. Unlike Earth, which gets most of its energy from the Sun, Jupiter actually radiates more heat from its interior than it receives from sunlight. Deep in Jupiter's atmosphere, the pressure and temperature increase rapidly. The clouds we see in photographs are only the uppermost layer. Beneath them are layers of water clouds, and beneath those, conditions grow increasingly extreme, hot, dense, and strange, pressing down toward a core that may be a solid or semi-solid mixture of rock and metal, compressed to a density that has no parallel on Earth. The atmosphere, which looks so simple and banded from outside, is in reality one of the most complex weather systems in the solar system, running continuously, a slow and ancient engine of wind and cloud. The layers beneath the beautiful surface are always the ones holding everything together. The Juno spacecraft has been orbiting Jupiter since 2016, sending back some of the most detailed images and measurements of Jupiter ever recorded. Juno travels in a highly elliptical orbit, swinging close to Jupiter every 53 days, before retreating to a safer distance from the intense radiation. During each close pass, it collects enormous amounts of data about Jupiter's atmosphere, magnetic field, and interior. Juno has revealed that Jupiter's atmosphere is far more complex than scientists expected. The bands and zones extend much deeper than previously thought, and the planet's core is not the neat, compact ball of rock and metal that older models predicted. Instead, the core appears to be diffuse, spread outward, as though the original solid core was dissolved and mixed into the surrounding layers over billions of years. Jupiter is more complicated on the inside than it looks from the outside, which is true of most things. Most things, when you look closely enough, turn out to be more layered and more mysterious than they first appear. Jupiter's cloud tops are intensely cold, reaching temperatures of around -145 degrees Celsius. Standing in those upper clouds, if you could somehow float there, you would feel cold unlike anything on Earth, in an atmosphere of hydrogen and helium and ammonia, beneath a sky filled with fast-moving cloud bands, with the sun reduced to a bright but distant star. Jupiter is more than 5 times farther from the sun than Earth is, so sunlight arrives faint and pale, diluted by distance, warming very little. The intense cold of Jupiter's upper atmosphere is one reason the clouds take on such distinctive forms. The chemistry there is different from anything we experience on Earth, producing crystals and particles and color compounds that exist nowhere else in our solar system. The pale oranges and creams and whites of Jupiter's clouds come partly from sulfur compounds, partly from ammonia ice, and partly from chemistry we still do not fully understand, driven by faint, cold sunlight on a world that mostly heats itself from below. There is a kind of beauty that comes only from cold and distance, and the slow work of chemistry in the dark. Jupiter takes almost 12 Earth years to complete one orbit around the Sun. Because of this, every 12 years Jupiter returns to roughly the same position in our night sky, visible against the same background of stars. Ancient civilizations used Jupiter's slow orbit as a kind of calendar. In Chinese astronomy, a 12-year cycle was built around Jupiter's journey through the zodiac, each year named for a different animal, corresponding to a different position of the planet. The Babylonians tracked Jupiter with careful precision, recording its movements across the sky on clay tablets. The Romans named it for their king of the gods, and the name stuck. All of that watching, all of that careful recording across thousands of years, was attention paid to the same slow, steady planet that is out there tonight, tracing its patient circle around the sun, unaware of any of the stories we have built around it. Ancient eyes watched the same slow light and found in it a quiet measure of time. Jupiter has a faint, diffuse glow that is not reflected sunlight. Part of the light Jupiter emits is thermal, actual heat radiation from its interior, a remnant of the energy released when Jupiter contracted from a diffuse cloud of gas into the dense, compressed world it is today. Jupiter is still slowly shrinking, contracting by about 2 centimeters per year as it radiates this ancient heat into space. Over billions of years, this internal heat has been one of the engines driving Jupiter's complex weather. Scientists sometimes describe Jupiter as a failed star, not because it came close to becoming one, but because it is made of the same raw materials as the Sun, hydrogen and helium, in roughly the same proportions. Jupiter simply did not have enough mass to trigger the nuclear fusion that turns a ball of gas into a star. So instead it sits there, quietly glowing with its own faint warmth, a world that carries the memory of its violent birth as a diffuse, contracting cloud of ancient gas. Even failed things carry warmth, ancient and faint, drifting outward into the patient dark. The pressure at Jupiter's core may be around 40 to 70 million times the atmospheric pressure at Earth's surface. Numbers like that are hard to hold in the mind. To give them some shape, the pressure at the deepest point of Earth's oceans is about 1,000 times the pressure at sea level, and even that is enough to crush most objects. The pressure at Jupiter's core is tens of millions of times greater than that. Under such conditions, hydrogen, a gas at room temperature and pressure, becomes a metal. It conducts electricity. It flows in vast currents. It generates Jupiter's immense magnetic field. The boundary between the gaseous outer atmosphere and the liquid metallic hydrogen interior is not a sharp line, but a gradual transition, a slow deepening, a continuous compression where one state of matter bleeds into another. There is no surface to land on. There is only descent, slow, continuous, into heat and pressure and darkness, until something like a solid core may exist at the very bottom, warm and ancient and utterly unreachable. Some depths are not meant to be reached, only quietly imagined from a comfortable distance. Jupiter's 4 Galilean moons are locked into a gravitational resonance with each other. Io completes 4 orbits of Jupiter in the same time it takes Europa to complete 2, and in the same time it takes Ganymede to complete 1. This is called a Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who described it in the 18th century. It is not a coincidence. It is a gravitational arrangement that has been self-reinforcing over billions of years, each moon tugging on the others in ways that keep them locked in their precise ratio. This resonance is what generates the tidal heating of Io, keeping its interior molten. It may also contribute to the subsurface ocean of Europa. The moons do not know they are dancing together in this precise, ancient rhythm, but the mathematics is there, quiet and exact, a harmony built from gravity and time that has been running without interruption for longer than complex life has existed on Earth. There is a kind of music in the solar system that does not need to be heard to be real. Callisto, the outermost of the 4 Galilean moons, is the most heavily cratered body in the solar system. Its surface is ancient, so old that it has not been renewed by geological activity for billions of years, and every impact over that vast span of time has left its mark. Where Io is constantly resurfaced, and Europa shows relatively few craters, Callisto is a record of everything that has struck it, a surface that reads like a history written in stone. Scientists value Callisto, partly for this reason. It is a kind of archive, preserving the story of bombardment in the early solar system in a way that more geologically active worlds cannot. Callisto orbits at a comfortable distance from Jupiter, far enough to mostly escape the tidal heating that drives activity on the inner moons, and it drifts quietly in its orbit, wearing all of its ancient scars without complaint, patient and still. Quietly, it carries every mark the past left on it, and keeps going anyway. Jupiter emits radio waves. When its magnetic field traps and accelerates charged particles, particularly from Io's volcanic emissions, those particles generate powerful bursts of radio emission that can actually be detected on Earth with a simple radio receiver tuned to the right frequency. In the 1950s, astronomers discovered these radio bursts accidentally, not knowing at first what was generating them. The sounds, when converted to audio and played through a speaker, are eerie, crackling, sweeping bursts of static that have a strange, almost alive quality. Some of the emissions have been recorded and shared publicly, and listeners often describe them as otherworldly, like signals from something vast and ancient and indifferent. Jupiter is not trying to communicate. It is simply doing what physics dictates, accelerating particles in a magnetic field, producing radiation. But in the quiet dark of a room at night, the idea of Jupiter making sounds that reach us here, across hundreds of millions of miles, carries a strange and gentle weight. You are still, and yet you are moving, and somewhere beyond the dark, Jupiter hums. The Shoemaker-Levy 9 comet collided with Jupiter in July of 1994, in one of the most dramatic astronomical events ever directly observed. The comet had been captured by Jupiter's gravity years earlier, and had broken apart into a chain of 21 fragments as it orbited. When it finally fell, the fragments struck Jupiter one by one over the course of 6 days, each impact releasing energy equivalent to hundreds of nuclear weapons. The impacts left dark scars in Jupiter's cloud tops that were visible for months through Earth-based telescopes. For the first time, humanity watched in real time as a solar system collision unfolded, confirming what scientists had long theorized, that Jupiter's gravity makes it a target, and that target-absorbing role has profound implications for the history of life on Earth. The scars eventually faded, absorbed back into the churning atmosphere, as though the planet had simply swallowed what came and continued turning. Everything that strikes something large enough eventually becomes part of it, lost in the quiet depth. Jupiter's atmosphere contains complex organic molecules, carbon compounds that are among the chemical building blocks of life. These molecules are not life themselves, but their presence in Jupiter's atmosphere tells us something about the chemistry of the early solar system, when these same molecules were scattered everywhere, falling onto young planets and moons, potentially seeding worlds with the raw materials for biology to eventually emerge. Jupiter is, in this sense, a kind of vast chemistry laboratory, mixing and processing complex molecules in its deep, turbulent atmosphere, driven by heat and pressure and lightning. Lightning, in fact, is common in Jupiter's atmosphere, crackling in powerful storms much deeper than the visible cloud tops. Some of those lightning bolts may be thousands of times more powerful than anything on Earth. In those flashes, in those brief and ancient moments of electricity and heat, chemistry happens that we are still working to understand. Even in the dark and cold and pressure of a place no one has been, the universe quietly makes the building blocks of wonder. Jupiter's great red spot has been shrinking and changing shape for decades. In the 1800s, when astronomers first began recording its dimensions carefully, the storm was enormous, wide enough to contain 2 or 3 planets the size of Earth, with room to spare. By the early 21st century, it had shrunk to roughly the diameter of Earth, still large by any measure, but dramatically smaller than its former self. The storm has also changed shape, moving from an oval to a more circular form. What is causing the shrinkage is not entirely clear. Some researchers believe the storm is absorbing smaller vortices that slow its rotation and reduce its energy, while others think changes in the jet streams surrounding it are gradually starving it of the energy it needs. The Great Red Spot may eventually disappear entirely. The oldest storm we know of may simply stop one day, not dramatically, not all at once, but gradually, quietly, fading the way most ancient things eventually fade. Ancient storms do not always end in violence. Sometimes they simply grow still, and the clouds close over them like sleep. Deep inside Jupiter, under layers of gas and liquid and metallic hydrogen, there may be a core made of rock and metal, compressed to densities far beyond anything on Earth. For decades, the standard model of Jupiter pictured a relatively compact, dense core at the center, a ball of heavy elements, left over from the initial planetesimal that first formed and then swept up the surrounding gas. But data from the Juno mission has complicated that picture. The core appears to be larger and more diffuse than expected, what scientists now call a fuzzy core, suggesting that at some point in Jupiter's past, a large object may have struck the planet and partially disrupted and mixed the original core material outward. So even Jupiter's most ancient, deepest, most fundamental part is not what we thought it was. It is older and stranger, and less defined than our models assumed, which is perhaps the way it should be. The oldest parts of things are often the hardest to see clearly, even when you are looking directly at them. Jupiter and the Sun share more than just a solar system. They share a composition. Both are made primarily of hydrogen and helium in roughly similar proportions, because both formed from the same ancient cloud of gas and dust. The difference between Jupiter and the Sun is, at root, a difference in mass. The Sun contains about 1,000 times the mass of Jupiter. That additional mass generated the gravity needed to compress hydrogen tightly enough to begin nuclear fusion, the process that makes stars shine. Jupiter, with its lesser mass, never reached that threshold. It came close, in the cosmic sense. It is the largest planet in the solar system by a considerable margin, and it has more mass than all the other planets combined. But close is not enough when it comes to becoming a star. So Jupiter became something quieter, a giant, cold, ancient world circling the star it never quite was. Some things spend their whole existence near the light, without ever needing to produce it themselves. Europa's surface ice is constantly being churned and renewed by tidal stress. The same gravitational squeezing that keeps Europa's interior warm also cracks and reshuffles its icy crust, erasing craters and producing the distinctive network of brown lines, called linea, that cross the moon's surface. These lineae form where the ice cracks and then refreezes, often with darker material pushed up from below, seeping into the gaps. Some researchers believe that the dark material in these cracks contains organic compounds from the ocean below, chemistry being brought to the surface by the constant movement of the ice. If that is true, then the surface of Europa is not just ice. It is a slow-moving record of what is happening in the dark ocean underneath, written in a script of brown lines on white ice, waiting for us to learn to read it. We sent a spacecraft toward Europa, the Europa Clipper, launched in 2024, to begin that reading. Somewhere in the dark, a patient ocean waits to have its story slowly understood. Jupiter's atmosphere contains 3 distinct cloud layers. The topmost layer, the one visible in photographs, is made of ammonia ice crystals. Beneath that is a layer thought to be made of ammonium hydrosulfide, a compound that gives some of Jupiter's cloud regions their brownish color. And beneath that is a third layer thought to be made of water ice and possibly liquid water droplets. Each layer occupies a different band of altitude and temperature, interacting with the others through the powerful vertical circulation of the planet's weather systems. The colors in Jupiter's clouds, the oranges and browns and whites and pale creams, come from chemical reactions between these compounds and trace elements, some of which we have identified and some of which we have not. Jupiter's palette is painted by chemistry, slowly and constantly, in a cold and distant dark, producing something that happens to look beautiful to a species that evolved on a small, warm, rocky world more than 400 million miles away. Beauty does not require an audience. It simply requires the right conditions and time. The moon Callisto orbits Jupiter at a distance of about 1.2 million miles, farther than any of the other Galilean moons, and far enough from Jupiter's intense radiation belts to make it one of the safest places in the Jovian system for potential human exploration. Callisto has no significant internal activity, no volcanoes, no tidal heating, no geological churning, which means its surface is stable and predictable in a way that Io and Europa are not. Some mission planners have imagined Callisto as a potential base for humans exploring the outer solar system, a quiet, stable world from which you could observe Jupiter and conduct research on the Galilean moons without being constantly bathed in lethal radiation. It would be cold there, very cold, in the permanent shadow of Jupiter, and the sun would be a distant, unremarkable star. But Callisto would be calm and ancient and enduring, which has its own quiet appeal. There is a kind of safety in stillness, and a kind of rest in a world that has not changed in a very long time. Jupiter influences the orbits of asteroids in ways that protect Earth. The asteroid belt, that ring of rocky debris between Mars and Jupiter, is shaped partly by Jupiter's gravity. Objects in certain orbital resonances with Jupiter are regularly nudged out of stable orbits and sent elsewhere, some falling toward the Sun, some ejected from the solar system, and occasionally, some directed toward the inner planets. This is the other side of Jupiter's protective role. It can both shield and endanger the inner solar system, depending on the circumstances. But over the long arc of solar system history, the net effect has been beneficial for Earth. Jupiter has been called a cosmic vacuum cleaner and a gravitational shepherd. Both names capture something true about it. It cleans up, it redirects, it shapes the neighborhood through pure gravitational presence, without intention, without awareness, simply by being massive and close enough to matter. The things that shape our world most profoundly are often the ones farthest away and most indifferent to us. The temperature at Jupiter's core is estimated to be between 30,000 and 50,000 Kelvin, several times hotter than the surface of the Sun. This enormous internal heat is the legacy of Jupiter's formation. The gravitational energy released when billions of smaller objects collapsed together to form the planet was converted to heat, and that heat is still slowly leaking out, billions of years later. Jupiter is like a slowly cooling ember from the early solar system, carrying warmth from an epoch so ancient it predates the Earth by tens of millions of years. The heat leaks outward through convection, through the slow rise and fall of hot gas in Jupiter's interior, driving the atmospheric circulation that produces the bands and zones and storms we observe. It is the ghost of the planet's violent birth, still warm, still rising, still shaping the surface of the world it gave rise to. Quietly, the warmth of an ancient beginning still shapes everything above it. Jupiter's rings were likely formed from material ejected by 4 small inner moons, Metis, Adrastea, Amalthea, and Thebe, when they were struck by micrometeoroids. This is why Jupiter's rings are made of dark dust, rather than the bright ice that composes Saturn's rings. The dust is constantly being lost, spiraling inward toward Jupiter under the influence of the planet's magnetic field, and constantly being replenished by new impacts on the source moons. The rings are in a dynamic equilibrium, always changing at the smallest scale, always roughly the same at the large scale, maintained by the same slow, continuous physics that has been running for millions of years. If the supply of impact ejecta from the inner moons stopped, Jupiter's rings would fade and disappear within a few thousand years, vanishing as quietly and invisibly as they formed, leaving no record of themselves in the Jovian dark. Some of the most delicate things in the universe persist only because of a continuous, quiet effort to replace what is lost. Jupiter has a very faint aurora. Like Earth, Jupiter has aurora, glowing curtains of light where charged particles from the solar wind enter the atmosphere along magnetic field lines and excite atoms into emitting light. But Jupiter's aurora is far more intense and extensive than Earth's, covering an area larger than the entire surface of the Earth. Unlike Earth's auroras, which depend heavily on solar wind activity, Jupiter's aurora is driven largely by Io, the volcanic moon constantly spewing sulfur dioxide gas into space, some of which gets ionized and swept into Jupiter's magnetic field, creating a continuous flow of charged particles that power the aurora nearly continuously. The aurora glows in ultraviolet light, largely invisible to the naked eye, but beautiful in images taken by the Hubble Space Telescope. Great sweeping arcs of invisible light wrapping around Jupiter's poles, faint and constant, while the rest of the planet turns below them. The universe is full of lights, too faint or too distant for us to see, burning quietly in the dark regardless. Ganymede is the only moon in the solar system known to have its own magnetosphere. Most moons have no significant magnetic field. They are too small and geologically inactive to generate one. But Ganymede, despite being a moon, has a liquid iron core that generates a weak magnetic field, creating a small magnetosphere nested inside Jupiter's much larger one. The interaction between Ganymede's magnetic field and Jupiter's creates a fascinating, complex system, with field lines connecting the two bodies, and aurora on Ganymede, powered by the interaction between the two magnetic environments. The Hubble Space Telescope observed these aurora shifting in response to Jupiter's magnetic field, which allowed scientists to infer the presence of Ganymede's subsurface ocean, because the ocean's salt water would conduct electricity and damp the oscillations of the magnetic field in a characteristic way. A hidden ocean, discovered by watching lights dance in a magnetic field around a moon circling a gas giant, 480 million miles from where you are lying right now. The universe finds patient and indirect ways to reveal its secrets to the ones willing to look carefully enough. Jupiter's upper atmosphere experiences lightning on a scale far exceeding anything on Earth. Lightning on Earth occurs when charge separation builds up in storm clouds, typically in large thunderstorms over tropical regions. On Jupiter, lightning is detected deep in the atmosphere, in regions thought to contain water clouds. The bolts are estimated to be thousands of times more powerful than typical Earth lightning, and they occur in polar regions more than at Jupiter's equator, the opposite of Earth's pattern. The Juno spacecraft, flying close to Jupiter, has been able to detect the radio signals produced by these lightning bolts with much greater clarity than previous missions. The audio recordings of Jovian lightning, converted from radio signals, have a slow, haunting quality, drawn-out, rumbling bursts that sound less like the sharp crack of an Earth thunderstorm and more like something vast and patient, speaking to itself in a language we cannot parse. Tonight, while you breathe slowly, vast storms are speaking to themselves in the dark, billions of miles from here. Jupiter's magnetosphere, the region of space dominated by its magnetic field, is the largest structure in the solar system other than the heliosphere, the Sun's own magnetic bubble. If you could see Jupiter's magnetosphere with your eyes, it would appear larger than the full moon from Earth. On the side facing the Sun, the solar wind compresses it to a distance of about 3 million miles. On the opposite side, it extends into a long magnetotail, stretching hundreds of millions of miles downstream, past the orbit of Saturn at times. Inside this vast magnetic envelope, the physics is complex and dynamic. Charged particles spiral along field lines, radiation belts form and pulse, and the moons of Jupiter are continuously bathed in radiation that would be lethal to unprotected life. Jupiter's magnetic world is invisible to the naked eye, but it is real and immense, and it fills the space around the planet the way a quiet atmosphere fills the space around a mountain. The invisible things around us take up more space than the things we can see. Io's volcanic plumes reach heights that would place them in near space if they occurred on Earth. Some of the largest plumes extend over 300 kilometers above Io's surface, high enough, if scaled to Earth, to reach far into orbit. The material ejected by Io's volcanoes enters space and forms a torus, a donut-shaped ring of gas and plasma, around Jupiter, following Io's orbit. This Io-plasma torus is one of the most prominent features of Jupiter's magnetic environment, constantly feeding charged particles into the magnetosphere and contributing to the aurora and radiation belts. Io produces roughly 1 ton of material per second through its volcanic activity, all of which eventually enters this torus. The torus glows faintly in ultraviolet and optical light, a ghostly ring circling Jupiter at the orbit of Io, an invisible river of volcanic breath flowing through the cold dark of the Jovian system. A small, burning world breathes its fire slowly outward into the cold, and the dark receives it, patient and still. The interior of Jupiter is divided into layers, the way an onion is divided, but the layers bleed into each other without sharp boundaries. From the outside in, you first move through the atmosphere, where gas gradually thickens and the pressure rises. Then the gas transitions, smoothly, over depth, into liquid hydrogen, behaving more like a fluid than a gas. Deeper still, the hydrogen transitions into the metallic state, where it conducts electricity. And at the center, the fuzzy core, possibly a mixture of rock and metal, and diffuse heavy elements mixed into the surrounding layers. There are no hard edges, no surfaces, no places where you could stand and say, this is where one thing ends and another begins. Jupiter is a world of gradual transitions, continuous changes, everything shading slowly into everything else. There is something restful about that. The idea of a world without sharp edges, without abrupt changes, where everything deepens and thickens and shifts by slow degrees, endlessly. Some places change so slowly that the change itself becomes a kind of stillness. The Galileo spacecraft ended its mission in September of 2003 by deliberately plunging into Jupiter's atmosphere. After nearly 8 years of orbiting Jupiter and conducting the most comprehensive study of the Jovian system ever attempted, the spacecraft was running low on fuel, and there was concern about contaminating Europa with Earth microbes if it drifted there uncontrolled. So mission controllers sent a final command, and Galileo fired its engines, and slowly, over a period of hours, it fell toward Jupiter. It would have entered the atmosphere at 60 kilometers per second, experiencing deceleration forces hundreds of times gravity, before being crushed and vaporized in the increasing pressure and heat of the deeper atmosphere. The scientists who built Galileo and spent years analyzing its data watched its final signals fade from their screens, and then the spacecraft was gone, consumed by the planet it had studied, become part of Jupiter, its atoms mixed into those deep, churning clouds. A quiet ending for a long, patient mission. Everything that goes far enough eventually finds its way back into the deep and rests there. Jupiter is surrounded by a swarm of small moons in distant, irregular orbits, the so-called irregular satellites, most of which are thought to be captured objects from the early solar system, ancient planetesimals, or fragments of larger bodies that wandered too close to Jupiter's gravity and never escaped. These outer irregular moons are so small and so dark that many of them were discovered only in the last few decades, when advances in telescope technology made it possible to detect objects of their size at Jupiter's distance. Some of them orbit in the same direction as Jupiter rotates. Others orbit in the opposite direction, retrograde, suggesting they were captured from different populations of early solar system objects, coming from different directions, falling into Jupiter's gravity at different times across billions of years. They are the oldest residents of Jupiter's neighborhood, silent and dark, circling slowly in their long, tilted orbits, carrying the chemistry and history of the early solar system in their cold, ancient rock. The oldest ones are always the quietest, drifting in long, slow arcs at the edge of the light. The Great Red Spot produces winds that rotate counterclockwise in Jupiter's southern hemisphere. Like all large storm systems in rotating planets, the Great Red Spot is a vortex, a self-sustaining circulation driven by the temperature difference between its interior and its surroundings. The storm rotates with a period of about 7 Earth days. Its winds at the edges reach speeds of around 450 miles per hour, making it far more powerful than any hurricane on Earth. And yet, despite this violence, the storm maintains its oval shape and its position in Jupiter's southern hemisphere with remarkable stability, anchored by the jet streams above and below it. The precise mechanism that maintains its shape and energy over centuries is still debated among scientists. It may be feeding on smaller vortices, absorbing their energy. It may be drawing heat from deeper in the atmosphere. It simply keeps turning, patient and enormous, in the clouds of a world too far away to feel. Even the wildest storms, at the right distance, look patient and still against the dark. Rest here for a moment. There is more to come. The ammonia ice crystals in Jupiter's upper clouds drift in bands so wide that a single band could swallow the Pacific Ocean. Beneath those drifting crystals, the air thickens into something no aircraft could fly through. A pressure so gradual and so complete that descent would feel less like falling and more like being slowly held. Scientists have mapped these bands from the outside, tracing their colors and their speeds, learning the patterns without ever being inside them. We know the temperatures and the chemical compositions. We know where the clouds thin and where they pile up into towering storm columns. We know the broad shapes of things, from a careful, distant watching that spans generations of scientists. And in that knowing without touching, in that understanding assembled from light and radio waves and careful inference, there is a kind of patience that mirrors something in the deep, slow turning of the planet itself. Some knowledge arrives quietly, over years, in small pieces, until it is enough. Europa's ocean, if it exists as scientists believe, may be one of the most habitable environments in the solar system beyond Earth. Not because it is warm. It is not. At least not by the standards of life as we know it here. Not because it has sunlight. None reaches that deep beneath the ice. But because it likely has liquid water, it likely has chemistry, and it may have hydrothermal vents on its seafloor, cracks where the moon's internal heat escapes, where chemical reactions create gradients of energy that life on Earth has learned, again and again, to exploit. The deep ocean vents on Earth, discovered in 1977, were the first evidence that life could exist without sunlight at all, that in the cold dark at the bottom of the sea, entire ecosystems could thrive around the heat and chemistry of a volcanic vent. If life found that niche on Earth, the possibility that it has found a similar niche on Europa becomes harder and harder to dismiss with certainty. The dark is not empty. Sometimes the dark is exactly where life decides to begin. Jupiter's magnetic field is so powerful that it accelerates particles to nearly the speed of light. In the radiation belts surrounding Jupiter, regions where charged particles are trapped and accelerated by the planet's rotating magnetic field, electrons can reach speeds close to 300,000 kilometers per second, near the upper limit that physics allows. These particles, when they strike the surfaces of the inner moons, strip away atoms, erode surfaces, alter chemistry. The surface of Europa, for instance, is constantly being bombarded by this radiation, which means anything that might live in Europa's ocean would need the ice above it as shielding, the same way Earth's atmosphere shields life here from the radiation of space. The ice is not just a cold covering over the ocean. It is armor. It is the thing that makes life below possible, if life is there. Jupiter's own magnetic field, which creates the radiation, also indirectly creates the conditions that might protect life from it. The universe is fond of this kind of arrangement, danger and shelter, woven from the same source. Even now, as you drift, a moon carries its ocean quietly beneath its ice, shielded by the cold above and the warm below. Callisto's surface is a record of 4.5 billion years of impact history, essentially unchanged by the geological processes that have erased similar records on most other bodies in the solar system. Looking at Callisto is something like looking at a photograph of the early solar system, cratered and dark and densely packed with the marks of a time when objects were still colliding frequently, still finding their places in the gravitational order. Multi-ring impact basins, where a large object struck and the shock wave rippled outward through the ice, are among the oldest visible structures in the solar system. They have been sitting there, unchanged, since before complex life existed on Earth. Callisto is not exciting in the way Io is exciting, or Europa is intriguing. It is something quieter than that, a record, a witness, a patient moon that has simply been watching since the beginning, keeping its marks, keeping its silence, drifting in its wide, slow orbit around a gas giant that has itself been there since nearly the start. There is a kind of dignity in a world that keeps its scars and keeps going, quietly, for billions of years. Jupiter's atmosphere contains water, though observing it has proven difficult because the water is located deep beneath the visible cloud tops, in regions too hot and too pressurized for spacecraft to easily access. The Galileo probe, released in 1995, descended directly into Jupiter's atmosphere before being crushed by pressure. It detected less water than scientists expected, which puzzled researchers for years. Eventually, it was determined that the probe had entered an unusually dry region, a kind of Jovian desert, and that other parts of Jupiter likely have far more water. More recent Juno data has confirmed higher water abundances in different regions. Jupiter's water matters for the broader story of our solar system. Water ice was one of the key components of the disk from which planets formed, and understanding where it ended up, and in what quantities, helps scientists understand the history of that formation, and ultimately, the history of oceans on Earth. The water in the clouds of a distant giant, and the water in the sea below your window, can come from the same ancient source. The Juno spacecraft discovered that Jupiter's poles look completely different from its equatorial regions. Instead of the parallel bands and zones that dominate Jupiter's middle latitudes, the poles are covered in enormous cyclonic storms, circular vortices packed tightly together like cells in a honeycomb. At Jupiter's North Pole, 8 cyclones surround a central polar cyclone, each one larger than the continental United States. At the South Pole, 5 large cyclones form a pentagon around a central one. These storms have been remarkably stable since Juno first imaged them, maintaining their arrangement over years of observations. Why the polar storms arrange themselves in these geometric patterns is still an active area of research. The mathematics of fluid dynamics on a rapidly rotating planet produces these structures under the right conditions, but the details remain a subject of ongoing study. From above the pole of Jupiter, the planet looks nothing like the familiar striped world we see in most photographs. It looks instead like a dark, swirling collection of blue-gray eyes, each one enormous, each one ancient, each one quietly spinning. Seen from a new angle, familiar things reveal themselves to be stranger and more beautiful than we imagined. Jupiter has been observed to have lightning storms that last for months at a time. On Earth, even the most persistent thunderstorm systems dissipate within days. On Jupiter, Storm systems can lock into the atmospheric circulation and persist for seasons, years, or in the case of the Great Red Spot, centuries. Juno has detected lightning in and around Jupiter's polar regions, deep, powerful electrical discharges in the water clouds far below the visible ammonia tops. Some of these storm systems are visible in Juno's images as bright white ovals embedded in the darker polar regions, convective upwellings where warm gas rises rapidly from below, carrying moisture and charge with it, generating the lightning as it goes. These storms are embedded in the broader circulation, like features in a river, turning slowly with the flow, sustained by a continuous supply of heat from Jupiter's interior. They are patient in the way all Jovian things are patient, running on a timescale that makes human weather feel like the blink of an eye. The universe keeps its storms running long after we have named them and moved on. The universe is patient, so are we. The ammonia crystals that drift through Jupiter's upper atmosphere are not uniform in size or shape. They form and dissolve continuously, shaped by the turbulence of the cloud systems around them, growing where the atmosphere cools and ascending gas brings fresh ammonia vapor, dissolving where descending gas warms and dries the air around them. Scientists have modeled these crystal formation processes and found that Jupiter's ammonia clouds behave in some ways like Earth's cirrus clouds, the thin, wispy high-altitude ice clouds that sometimes streak across our sky on cold, clear days. There is something oddly intimate about that comparison, that a cloud on a gas giant 400 million miles away follows some of the same basic physics as the thin white streaks above your head on a winter afternoon. The universe uses its rules everywhere, without distinction, and in the most distant and alien places, it quietly echoes the familiar. Even now, as you drift, the same quiet physics that shapes a winter cloud above your window is shaping a cloud above Jupiter. The inner moons of Jupiter, the four small moons Metis, Adrastea, Amalthea, and Thebe, orbit so close to Jupiter that they complete their orbits in less than one Earth day. Metis, the innermost, orbits Jupiter in just over 7 hours. These moons are dark and irregular in shape, not round like the larger Galilean moons, but lumpy and elongated, tumbling slowly in their fast, close orbits. Amalthea, the largest of the four, is a dark reddish object about 270 kilometers long, shaped roughly like a potato, and it is thought to be covered in a layer of material that has been deposited from Io's volcanic plumes. It radiates more heat than it receives from the sun, not from internal activity, but because it is embedded in Jupiter's radiation belts, constantly being bombarded by energetic particles that warm it from the outside. It is a small, dark world, moving very fast in a very deep orbit, bathed in invisible radiation, drifting in a place where the sky is dominated entirely by the enormous pale disk of Jupiter above it. Some places are so deep inside something vast that the vastness becomes the whole sky. Jupiter's magnetic axis is tilted relative to its rotational axis by about 10 degrees, smaller than Earth's magnetic tilt, but significant enough to produce a wobbling magnetic field that sweeps through space as Jupiter rotates. This wobble drives variations in the radiation environment experienced by Jupiter's moons, with the radiation intensifying and easing as the magnetic field sweeps past. For Io, which is constantly shedding material into the plasma torus, the interaction between its volcanic output and Jupiter's rotating magnetic field is so strong that it generates electric currents, tubes of current called flux tubes, connecting Io to Jupiter's poles. These flux tubes carry enormous amounts of electrical energy, enough, by some estimates, to power the entire electrical consumption of the United States many times over. They light up Jupiter's auroras. They connect a small volcanic moon to a giant planet across hundreds of thousands of miles of empty space, quietly, continuously, in the dark. The quiet connections between things, the invisible threads, carry more power than the things we can see. Europa's surface temperature averages around -160 degrees Celsius on the sunlit side, and colder still in shadow. It is a world of beautiful, deadly cold, a frozen shell above a potentially warm and living ocean. The surface ice is thought to be between 15 and 25 kilometers thick in most places, though there may be thinner regions where the ocean below comes closer to the surface, and where material exchanges between ocean and surface are possible. These thin spots, if they exist, are places of particular scientific interest, potential windows into whatever is happening in the ocean below, places where the chemistry of a hidden sea might be readable in the composition of the ice above it. The Europa Clipper mission, on its way to the Jovian system, is designed partly to search for these thin ice regions, to map them, and to analyze the surface chemistry of the ice as a proxy for what lies beneath. It will arrive in the orbit of Jupiter and begin its patient work of observation, flying past Europa dozens of times, each pass adding to a picture that will take years to assemble. The patient work of understanding happens slowly, one careful pass at a time, in the cold and the dark. Jupiter has no seasons. Because its axial tilt is only about 3 degrees, almost perfectly upright relative to its orbit around the Sun, the two hemispheres of Jupiter receive essentially the same amount of sunlight all year round. On Earth, our 23-degree tilt gives us the full cycle of seasons, the long days of summer, and the short, cold days of winter. Jupiter has none of that variation. Its climate, to the extent that word applies to a gas giant, is driven by its internal heat and by its rapid rotation, not by any seasonal variation in sunlight. The Great Red Spot, which sits in the southern hemisphere, experiences essentially the same solar irradiance year-round. The storm systems at Jupiter's poles see the same dim, cold Jovian sunlight in every month of every one of Jupiter's 12-year orbital periods. There is something deeply restful about the idea of a world without seasons, without the urgency of summer ending, without the cold reminder of winter coming. Just an endlessly even, dim, quiet light, the same today as it was yesterday and will be tomorrow. Some places rest in an eternal, even stillness, without the push and pull of changing seasons. The Jovian system, Jupiter and all its moons together, contains more water in total than exists on the entire surface of the Earth. Most of this water is locked in the ice shells of the Galilean moons, particularly Europa, Ganymede, and Callisto, each of which is thought to harbor vast subsurface oceans. Ganymede alone may contain more liquid water than all of Earth's oceans combined. The outer solar system, once thought to be a cold and dry and lifeless region, turns out to be rich in the one compound most associated with life as we know it: water. It arrived there in the early solar system, carried in the bodies of comets and planetesimals that formed beyond the snowline, the distance from the young sun, where temperatures were low enough for water ice to form and persist. All of that water has been sitting there, quiet and frozen, for over 4 billion years, wrapped in ice shells, resting in the dark. Quietly, the cold places of the solar system have been holding more water than we ever imagined. Jupiter's storm systems extend far deeper into the atmosphere than previously known. Data from Juno's microwave instrument, which can peer beneath Jupiter's visible cloud tops to depths of several hundred kilometers, has revealed that the belt and zone structure of Jupiter's atmosphere, the parallel bands of different colors, is not just a surface phenomenon. The bands extend downward, deepening and shearing against each other, for at least 3,000 kilometers below the cloud tops, far deeper than scientists expected. Below that depth, Jupiter's interior appears to rotate more uniformly. The deep interior turns more as a rigid body, while the outer atmosphere is a chaotic, layered system of competing winds. The transition between these two regimes, the turbulent, banded outer atmosphere and the more uniform deep interior, occurs in a region scientists call the shallow weather layer, a term that sounds almost modest, given that the layer in question is 3,000 kilometers deep. Jupiter makes everything a matter of scale. When everything is vast enough, even the shallow things run deep. The moon Io orbits Jupiter so quickly that a year on Io, one complete orbit of Jupiter, lasts only about 42 hours. In one Earth week, Io completes more than 4 orbits of Jupiter. This rapid orbit is what drives the tidal heating that keeps Io's interior molten. Jupiter's gravity flexes Io as it moves through its slightly elliptical orbit, squeezing and releasing it like a stress ball, generating heat through friction in the rock and magma of the interior. Io has no water. The heat and radiation have driven away any water that might once have been present, making it one of the driest places in the solar system. Its surface is dominated by sulfur in various forms, which gives it its distinctive yellow and orange and white and red coloring, like a world painted in the palette of fire and sulfur and heat. It is the most geologically active world we know, and it is also, perhaps paradoxically, one of the most inhospitable, a world that never stops changing, never cools, never settles. Even now, as you drift, a small world turns restlessly around the dark face of a patient giant. The orbital resonance between Io, Europa, and Ganymede is not only precise, but self-maintaining. If any of the 3 moons were to be perturbed, nudged slightly faster or slower by an external impact, the gravitational interactions between them would gradually pull the system back toward its resonant ratios. The resonance is what mathematicians and physicists call a stable equilibrium, a configuration that naturally resists small disturbances and returns to its resting state. It is one of the most beautiful examples in the solar system of a system that has found its own natural balance and holds it, not through any active process, but through the passive, continuous action of gravity. The 3 moons have been dancing in this precise, stable rhythm for billions of years, each one pulling on the others in ways that keep them locked in their ancient ratio, 4 to 2 to 1, orbiting Jupiter in a pattern that will likely continue for billions of years more, long after anything watching them has ceased to exist. The universe keeps its quiet rhythms long after the ones who notice them have gone. Jupiter was likely responsible for the late heavy bombardment, a period about 3.9 billion years ago when the inner solar system experienced a dramatic increase in impacts. One leading theory, called the Neis model, suggests that in the early solar system, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were not in their current orbits. A gravitational instability caused them to shift, and Jupiter's migration during this period would have destabilized the asteroid belt and sent enormous numbers of asteroids and comets raining down on the inner planets. Evidence for this bombardment is preserved in the crater-saturated surfaces of the Moon, Mars, and Mercury. On Earth, if it happened at all, the scars were erased by the planet's active geology. But the event itself, 3.9 billion years ago, may have been important for life, delivering water and organic compounds to the young Earth at a critical time in the planet's development, even as it also battered the surface repeatedly with devastating impacts. The things that hurt and the things that help often arrive together from the same dark direction. The pressure at the boundary, where Jupiter's gas becomes liquid, is roughly 1 million times atmospheric pressure at Earth's surface. At that depth, the distinction between liquid and gas becomes meaningless. The hydrogen is in a supercritical state, where it has properties of both simultaneously, and the transition from one to the other happens without any phase boundary, without any surface, without any visible change. You would simply descend, and the air around you would grow denser and hotter and more resistant, and at some point you would realize that what you were moving through was no longer behaving like a gas at all, but still, you could not say exactly when that had happened or where the line was. Some transitions are like that, gradual enough that you only notice them when you are already well past the point of no return, descending into something new, without a clear moment of crossing over. Tonight, While you breathe slowly, notice how sleep arrives the same way. Not all at once, but gradually, until you are already there. Ganymede's subsurface ocean is sandwiched between two layers of ice above it and high-pressure ice below it. This is different from Europa, where scientists believe the ocean sits directly on a rocky seafloor that might host hydrothermal activity. On Ganymede, the pressure at the base of the ocean is high enough to cause water to freeze into a denser form of ice. Ice seas, or Ice 7, forms that only exist under extreme pressure and are denser than liquid water, which is why they form at the bottom rather than floating to the top. This means that Ganymede's ocean may be isolated from its rocky interior by a layer of exotic ice, limiting the chemical exchange between rock and water that might otherwise support life. Scientists debate whether life could still exist there. Perhaps the answer is that we simply do not know enough yet. The universe keeps its deepest chemistry hidden in places we have not yet reached, beneath ice we have not yet drilled, in oceans we have not yet touched. The deepest things rest quietly beneath layer after layer of patient cold. Jupiter's clouds are not silent. Deep in the atmosphere, below the visible layer, convective storms generate infrasound, very low-frequency sound waves that propagate through the dense gas. These sound waves are well below the range of human hearing. They are felt rather than heard, vibrations rather than tones. Scientists have modeled what Jupiter's deep atmosphere would sound like at audible frequencies, and the result is something like a deep, slow rumbling, punctuated by the crackle of lightning and the whoosh of vast wind currents. The entire planet is, in a sense, continuously humming to itself, a deep, subsonic vibration rolling through its layers, driven by heat from below and the constant motion of gas above. The hum is inaudible from space and inaudible from Earth, but it is there, inside Jupiter, a sound no one has ever heard, traveling through a medium no one has ever entered, in a world that has been making that sound for 4.5 billion years. Somewhere in the dark, something vast hums quietly to itself, and the sound goes nowhere, and that is enough. Jupiter's atmosphere, when viewed in ultraviolet light, reveals features invisible to the human eye. Ultraviolet observations show distinct regions of ammonia ice that are brighter than their surroundings, regions where fresh ammonia is being lofted upward from below, creating young, bright clouds that stand out against the older, darker surroundings. These bright regions have been compared to thunderstorm anvils on Earth, the flat-topped, high-altitude clouds that mark the tops of powerful convective storms. On Jupiter, these convective towers are enormous. Each one may be hundreds of kilometers across, rising tens of kilometers into the atmosphere. The Juno spacecraft has imaged these convective storms in detail during its close passes, revealing that they are more complex and more organized than earlier observations suggested, nested within larger circulation patterns, constrained by the jet streams above and below them, shaped by a planet-wide system that has been running without interruption since Jupiter first formed. The universe is patient in its architecture, every small storm nested in something larger, every layer held by the one below it. The 4 Galilean moons are gravitationally locked to Jupiter. They always show the same face to the planet, the way Earth's moon always shows the same face to us. This tidal locking happens when the gravitational influence of a large body is strong enough to slow the rotation of a smaller orbiting body until its rotation period matches its orbital period. For Earth's moon, this process took hundreds of millions of years. For the Galilean moons, closer to a much more massive Jupiter, the locking happened more quickly. The result is that each Galilean moon has a permanent day side, always facing Jupiter, and a permanent night side, always facing away. On the Jupiter-facing side of Europa, the enormous disk of Jupiter dominates the sky, glowing with reflected sunlight, 4 times the diameter of the full moon as seen from Earth. On the far side, Jupiter is permanently below the horizon. The sky is dark, and the stars are all there is. Two faces, two eternities, on the same small world. Every world has a side that faces the light, and a side that rests in the ancient dark. Jupiter's equatorial regions move faster than its polar regions, a phenomenon called differential rotation, caused by the fact that Jupiter is not a solid body. Because different latitudes can rotate independently, Jupiter's equator completes a rotation several minutes faster than its poles. This differential rotation is responsible for the shearing forces that create the boundary between Jupiter's belts and zones, the dark and light bands that give Jupiter its characteristic striped appearance. Where gas at different latitudes moves at different speeds, turbulence develops along the boundary, producing the complex swirls and eddies visible in detailed photographs of Jupiter's cloud tops. The Great Red Spot sits in one of these boundary regions, which is part of why it has survived so long. It is anchored by the jet streams on either side of it, constrained in latitude, unable to drift north or south, held in place by the same differential forces that created it. Sometimes the things that confine us are also the things that hold us in place long enough to last. The Galileo probe that descended into Jupiter's atmosphere in 1995 was only about the size of a refrigerator. It entered the atmosphere at about 47 kilometers per second, roughly 17 times the speed of a rifle bullet, and experienced deceleration forces of about 230 times Earth's gravity during the initial entry phase. A heat shield absorbed and radiated the enormous energy of that entry, protecting the instruments inside long enough for the parachute to deploy and the probe to begin its slow descent through the clouds. It transmitted data for 57 minutes before the increasing pressure and heat crushed it. In 57 minutes, drifting under a parachute through the clouds of Jupiter, it changed our understanding of the giant planet profoundly, confirming the composition of the atmosphere, measuring the winds, detecting lightning. 57 minutes. The universe sometimes gives us very small windows of time in which to learn something vast. Some of the most important things we know were learned in a very small, very quiet window of time. Jupiter's northern and southern hemispheres are not mirror images of each other. Unlike Earth, where the weather patterns in the northern and southern hemispheres are broadly similar, Jupiter's two hemispheres have distinct and different cloud structures. The southern hemisphere contains the Great Red Spot and a different arrangement of belts and zones than the north. The poles look different from each other. The North Pole has 8 surrounding cyclones. The South has 5. Scientists are not certain why this asymmetry exists, whether it reflects differences in the deep interior circulation, or whether it is simply a long-lived pattern that happened to develop this way in the early history of Jupiter's weather, and has been maintained by the self-reinforcing dynamics of the atmosphere ever since. Jupiter's hemispheres are like two siblings who grew up in the same house and turned out quite differently, shaped by the same fundamental forces, but carrying their own particular histories in the patterns of their storms. Even things formed from the same source and circling the same center can develop in their own quiet, divergent ways. The sulfur dioxide ejected by Io's volcanoes forms a thin atmosphere around the moon. This atmosphere is ephemeral. It evaporates on the night side, where it freezes out onto the surface, and reforms on the day side, when sunlight warms the frost and turns it back to gas. Io therefore has an atmosphere that literally disappears on one side of the planet every day and reforms on the other, a breathing of sorts, though no creature breathes it and no life depends on it. The sulfur dioxide in this thin atmosphere is also continuously being stripped away by Jupiter's radiation and magnetic field, added to the plasma torus that circles Jupiter at Io's orbit. The torus, in turn, feeds material into Jupiter's magnetosphere, which distributes it outward and eventually loses it to the solar wind. A chain of matter, moving from the volcanic interior of a small moon, through space, into the magnetosphere of a gas giant, and eventually out into the interplanetary medium, all quietly, continuously, driven by nothing more than heat and gravity and the laws of physics. The universe moves its matter quietly from one form to another, always patient, never finished. Jupiter's gravity has shaped the Kirkwood gaps in the asteroid belt. The asteroid belt, which lies between Mars and Jupiter, is not uniform. It has regions of relative emptiness, called Kirkwood gaps, where very few asteroids orbit. These gaps occur at distances from the Sun, where an asteroid's orbital period would be a simple fraction of Jupiter's, 1/3, 2/5, 3/7, and so on. Asteroids that wander into these resonant positions are repeatedly nudged by Jupiter's gravity during each close approach, and over time, these nudges add up and destabilize the orbit, sending the asteroid elsewhere. The gaps are not maintained by any active process. They are simply the regions where Jupiter has, over billions of years, removed all the asteroids that were once there. They are absences shaped by gravity, empty spaces in the asteroid belt that mark, as clearly as a signature, the gravitational influence of a planet 400 million miles away. Quietly, the cosmos moves around you, and its empty spaces are as shaped and meaningful as the things that fill them. The light from Jupiter that reaches Earth is almost entirely reflected sunlight. Jupiter does not shine with its own visible light. When you see Jupiter in the night sky, a bright, steady, pale cream point of light, sometimes the brightest object in the sky after the Moon and Venus, you are seeing sunlight that has traveled roughly 500 million miles from the Sun, struck Jupiter's cloud tops, and then traveled another roughly 400 million miles to reach your eye. That light takes more than 40 minutes to make the journey from Jupiter to Earth. When you look at Jupiter, you are seeing it as it was 40 minutes ago. Its clouds in the positions they occupied 40 minutes ago. The Great Red Spot, either visible or not, depending on where it was in its rotation 40 minutes ago. Across the solar system, looking at something is always looking at the past. Distance and time are the same thing, written in light. Every light in the sky is a message from the past, arriving gently in the dark of the present. The moons of Jupiter experience solar eclipses regularly as they pass through Jupiter's shadow. Because Jupiter is so large, its shadow extends far into space. Io, Europa, and Ganymede all pass into Jupiter's shadow during each orbit, experiencing darkness for a period of time before moving back into sunlight. These eclipses were observed by the 17th century astronomer Ole Romer, who noticed that the eclipses of Io happened at slightly different times, depending on whether Earth was moving toward or away from Jupiter. He realized that the differences in timing were due to the time light takes to travel. When Earth was farther from Jupiter, the light announcing the eclipse had to travel farther to reach us. Using this observation, Romer made the first quantitative estimate of the speed of light in 1676. A shadow passing over a small moon, observed from a cold observatory in Denmark, revealed the speed of the thing that makes the universe visible. The universe hides its deepest truths in the most patient, unhurried observations. The patient ones, the ones who watch the same quiet event again and again, are the ones who find what others miss. Jupiter's Great Red Spot reaches higher into the atmosphere than the surrounding cloud systems. Observations from Juno have shown that the storm extends upward into Jupiter's stratosphere, producing a warm region, a kind of heat island, above the visible cloud tops. This is counterintuitive. You might expect the cool colors at the center of the storm to correspond to a cold region, but the opposite is true. The top of the Great Red Spot is warmer than its surroundings because of a process called adiabatic warming. The storm's dynamics pull stratospheric air downward into the vortex, and as that air descends and compresses, it warms. This warm cap above the Great Red Spot also produces a region of unusual chemistry, the ultraviolet light of the sun, reacting with molecules lifted by the storm into the upper atmosphere, creating complex organic compounds in the stratosphere of a gas giant. Jupiter is, in this way, a planet-scale chemistry experiment, running slowly and continuously. with results that emerge over millions of years. Long experiments yield the deepest results, and the universe is in no hurry to read them. The poles of Jupiter receive less sunlight than the equatorial regions, and yet the polar atmosphere is not colder than the equatorial atmosphere. In fact, Jupiter's poles are warmer than simple models predict. This is because heat from the planet's interior is redistributed through the atmospheric circulation, and because Jupiter does not rely on solar heating the way Earth does. The energy budget of Jupiter is fundamentally different from Earth's. Internal heat plays a comparable role to solar input, meaning the latitude-temperature relationship that governs so much of Earth's climate simply does not apply to Jupiter in the same way. The deep polar cyclones, those enormous, organized storm systems that Juno revealed, may play a role in this heat redistribution, carrying warm gas upward from below and redistributing it in the polar regions. Jupiter is a planet that heats itself from within and shares that warmth with even its darkest, most distant regions, a quiet internal fire, keeping the whole world just a little warmer than it would otherwise be. There is something tender in a world that carries its own warmth all the way to its coldest edges. Jupiter has been visited by 9 spacecraft to date. Pioneer 10 and Pioneer 11 flew past in 1973 and 74, the first human-made objects to visit the outer solar system. Voyager 1 and Voyager 2 followed in 1979, transforming our knowledge of the Jovian system. The Ulysses solar probe flew past Jupiter in 1992 to use the planet's gravity to alter its trajectory toward the poles of the Sun. The Galileo spacecraft arrived in orbit in 1995 and spent nearly 8 years there. The Cassini spacecraft flew past in 2000, on its way to Saturn. The New Horizons probe, en route to Pluto, used Jupiter for a gravity assist in 2007, and Juno arrived in orbit in 2016, still operating a decade later. 9 visits across 50 years, each one building on the last, each one revealing that Jupiter was stranger and more complex and more interesting than the one before had suggested. The planet repays attention. Every time we have looked more carefully, Jupiter has shown us something we did not expect to find. The outer irregular moons of Jupiter include several groups that likely originated as fragments of once larger objects that were broken apart by collisions. Astronomers have identified several dynamical families among the outer moons, groups of moons that share similar orbital characteristics, suggesting they are chips off the same ancient block. The Himalaya group, for example, consists of several moons that likely all came from a single precursor object that was disrupted by a collision billions of years ago. These fragment families are a kind of genealogy written in orbital mechanics. You cannot see the original object, which is long gone, but you can infer its existence from the family of fragments it left behind, still circling together in their slow, cold, distant orbits. Related by origin, though separated by distance. They drift in the outer dark of the Jovian system, like the scattered pieces of something that was once whole, patient, and small, and ancient. Some things are known only by what they left behind, faint traces, drifting in the quiet dark. Jupiter's atmospheric composition, mostly hydrogen and helium, with trace amounts of heavier elements, makes it what astronomers call a primitive solar composition object. This means its composition reflects, more closely than any other planet, the composition of the original solar nebula from which the entire solar system formed. The rocky inner planets have lost most of their hydrogen and helium over billions of years, their gravity too weak to hold these light gases against the heat of the Sun. Jupiter, with its enormous mass, has retained almost everything it gathered in the early solar system. It is, in a sense, a living fossil of the solar system's beginning, the closest thing we have to the original material, still in something like its original proportions, still circling the Sun in the outer dark, patient and primitive, and 4.5 billion years old. The oldest things in a system are often the ones that change the least, resting in their original form in the quiet dark. Europa's ocean, if life exists there, would represent life arising completely independently of life on Earth. A second Genesis, a separate experiment in biology, begun and run under entirely different conditions, with no connection to the origin of life here. The implications of that possibility are hard to overstate. It would mean that life is not a singular lucky accident that happened once, on one warm planet around one ordinary star. It would mean that life is something the universe does regularly, given the right conditions, chemistry and energy and liquid water, that life is less a miracle and more a tendency, a direction the universe moves in when conditions allow. Scientists are careful about these claims. We have found no life yet on Europa. We have not even confirmed the ocean's existence through direct measurement. But the possibility is real, and the universe does not need us to understand it in order to continue patiently arranging its chemistry in the dark. The universe continues while you sleep, running its quiet experiments in the cold and the dark. Jupiter's rotation rate was one of the first things measured about the planet with any precision. Astronomers in the 17th and 18th centuries noticed that Jupiter's cloud features moved across the visible disk, and by tracking the same feature over successive nights, they could measure how long Jupiter took to rotate. The measurement was surprisingly easy. Jupiter's rapid rotation means a feature on the equator moves measurably in just a few hours of observation. The first systematic measurements were made in the late 1600s, and they gave a rotation period close to the modern value of 9 hours and 55 minutes. Galileo himself, who discovered the Galilean moons in 1610, might have been able to measure Jupiter's rotation rate with his instruments if he had thought to track the cloud features carefully. The planet has been showing us its rotation, patiently and clearly, for as long as we have had telescopes to look through. The patient things reveal themselves to anyone who watches carefully enough and waits. The surface of Europa is thought to be geologically young, perhaps 40 to 90 million years old, based on the low density of impact craters. On a solar system timescale, that is recent, the dinosaurs were still alive on Earth when much of Europa's current surface was formed. This young age tells scientists that the surface is being continuously renewed. Old ice is being subducted or overridden by new material. The surface is in motion, turned over by the tidal forces and internal dynamics driven by Jupiter's gravity. The process is called resurfacing, and it has been running for as long as Europa has been orbiting Jupiter. The old ice goes down, the new ice comes up, and the surface is perpetually, slowly, being remade. Every few 100 million years, Europa presents a new face, not to any observer, since no observer is close enough, but to the cold, dark space around it, quietly cycling through its slow, tidal renewal. Quietly, even the frozen things are turning over, renewing themselves in the cold, patient dark. Jupiter's mass is 2.5 times the mass of all the other planets in the solar system combined. To understand what that means in terms of scale, imagine placing all of the other planets, Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, all of them together on one side of a cosmic scale, then place Jupiter alone on the other side. Jupiter is heavier, significantly heavier. This dominance of mass is what gives Jupiter its defining gravitational role in the solar system. Its ability to deflect comets, to shape the asteroid belt, to lock its moons in resonance, to generate the magnetic environment that encompasses a vast region of space. Jupiter's mass is the organizing fact of the outer solar system, in much the way the Sun's mass is the organizing fact of the entire solar system. Everything out there has been shaped, at least in part, by the gravity of this one enormous, ancient, gas-wrapped world drifting in the cold. The heaviest things in a system shape everything around them, quietly, without intention, simply by being what they are. The rest here for a moment. The universe is patient, so are we. The light that left Jupiter tonight will reach Earth in about 43 minutes. It will arrive quietly, unannounced, mixing with all the other light falling on the dark side of our planet, and no one will notice it specifically. No instrument will flag it as Jupiter light, different from the rest. It will simply arrive and be absorbed, the way all light eventually is. But for those 43 minutes, it was traveling, crossing the cold, empty distance between a gas giant and a small, rocky world, moving at the only speed the universe allows light to move, patient and constant, and indifferent to whether anyone was waiting for it. The universe does not send its light toward destinations. It simply sends it, and destinations receive it, or they do not, and the light does not know the difference. Even now, as you drift, light is crossing the dark between worlds, arriving whether or not anyone is watching. Jupiter's cloud bands change over years and decades in ways that still surprise scientists. Occasionally, one of the pale zones will darken, and a previously dark belt will fade, in a phenomenon called a belt disruption or revival. In 2010, Jupiter's south equatorial belt, one of the most prominent and consistent features of Jupiter's appearance, faded almost entirely, turning white, before gradually returning to its characteristic brown over the following year. The underlying cause involves the interplay between the visible ammonia ice cloud layer and a deeper deck of clouds. When conditions allow, the ammonia clouds thicken and cover the darker underlying layers, turning a region pale. Then, perhaps triggered by a large convective storm, the covering breaks up, the deeper, darker layers are revealed, and the belt returns. Jupiter wears different faces across the decades, shifting slowly, surprising the people who watch it most carefully, reminding them that even the things that look permanent are always quietly changing. The things that look most fixed are often the ones most slowly, silently, in motion. Io's largest volcano, Lokipata, is a lava lake roughly 200 kilometers across, larger than the state of New Jersey. It sits in a volcanic depression, a caldera, and its surface is a crust of cooled lava floating on a molten lake beneath. Periodically, this crust overturns, the cooled, denser surface sinks, and is replaced by fresh, hot lava welling up from below. This overturning happens on a cycle of roughly 500 days, and it can be detected from Earth by measuring the infrared brightness of Io. As the fresh lava is exposed, the heat output rises dramatically. Lokipatera has been overturning in this slow, periodic cycle for as long as we have had the instruments to detect it. A vast lava lake on a volcanic moon of Jupiter, rhythmically surfacing and resurfacing itself on a schedule that belongs to no calendar any human has ever used, driven by nothing but physics and heat and the patient pull of Jupiter's gravity. In the faint distance, something vast turns itself over slowly, renewing what was cooling, patient, and ancient, and quiet. Jupiter's magnetosphere interacts with the solar wind to create a boundary called the magnetopause, the surface where Jupiter's magnetic pressure exactly balances the pressure of the solar wind flowing outward from the sun. This boundary moves in and out as the solar wind strengthens and weakens, breathing in and out over periods of days. When a particularly strong burst of solar wind arrives, a coronal mass ejection from the sun, the magnetopause is pushed inward, compressing Jupiter's magnetic environment. When the solar wind weakens, the magnetosphere expands outward again. Jupiter breathes, magnetically, in response to the sun, a kind of long-distance relationship between the two largest objects in the solar system, the star and its giant companion, exchanging pressure across hundreds of millions of miles of empty space, each one subtly shaping the environment of the other across the slow, patient distance between them. The universe is full of long-distance relationships, quiet influences crossing vast space, felt rather than seen. The rings of Uranus, Saturn, and Jupiter all exist within the Roche limit of their respective planets, the distance within which tidal forces prevent material from coalescing into a moon. Any moon that wanders inside the Roche limit of a planet will be torn apart by tidal forces, its material scattered into a ring. Jupiter's small inner moons, Metis and Adrastea, actually orbit inside or near Jupiter's Roche limit, which is why they have not grown larger by accumulating material, and why they themselves are held together by internal strength rather than self-gravity. They are too small to be torn apart, but large enough to provide the material for Jupiter's rings. They exist in a delicate gravitational balance, inside the boundary where moons are torn apart, but strong enough to survive it, slowly feeding their outermost material into the rings that surround them. They are doing what the universe placed them to do, quietly, at the edge of disruption. Some things rest exactly at the boundary between breaking and holding, and they rest there for billions of years. The temperatures deep in Jupiter's atmosphere, below the water cloud layer, reach levels comparable to those in an industrial furnace. Down there, at pressures hundreds of times Earth's atmospheric pressure, the temperature climbs above 300 degrees Celsius, hot enough to melt lead, hot enough to vaporize most organic compounds. Yet even in those deep, hot layers, chemistry continues. Carbon compounds form and dissolve. Sulfur reacts with hydrogen to make hydrogen sulfide. Water vapor condenses into clouds and then evaporates again. The whole system is a vast, slow chemical processor, taking simple molecules and transforming them into more complex ones, then breaking them down again, driven by heat and pressure and the slow circulation of the atmosphere. In a way, Jupiter's deep atmosphere is doing what stars do, processing matter, transforming it, but at a cooler, slower, quieter pace. A star's engine running at very low power, in the dark, in the cold outer solar system, patient and ancient, and still going. Some engines run so quietly and so slowly that you would never know they were running unless you were very still and listened. Ganymede has surface features that record two distinct epochs of its geological history. The ancient dark terrain, which covers about a third of the surface, is heavily cratered, preserving the record of impacts from the early solar system, when collisions were far more frequent. The younger, brighter grooved terrain covers the remaining two-thirds and shows a different kind of geology, parallel ridges and troughs, produced by the stretching and fracturing of the icy crust, possibly driven by the same tidal forces that heat Io and warm Europa. The transition between these two terrains is sharp in some places and gradual in others, recording a period billions of years ago when Ganymede's interior was active enough to reshape large portions of its surface, and then gradually quieted. The geology of Ganymede is a story written in ice and time, a moon that was once busy and then, slowly, settled into the quiet stability it maintains today, ancient and scarred and still. Quietly, the cosmos moves around you, and a world of ice carries its old scars in patient, frozen silence. Jupiter's atmosphere contains phosphine, a compound of phosphorus and hydrogen that has no obvious source in a simple equilibrium chemistry model of Jupiter. On Earth, phosphine is produced by biological processes and by industrial chemistry, but also by lightning and heat. On Jupiter, the phosphine is thought to be produced deep in the hot interior and then lofted upward by convection before it has time to be destroyed by sunlight in the upper atmosphere. The presence of phosphine in Jupiter's atmosphere attracted attention in 2020, when the same compound was tentatively detected in the atmosphere of Venus, prompting speculation about biological sources, speculation that was later the subject of considerable scientific debate and revision. On Jupiter, the phosphine is almost certainly not biological, but its presence is a reminder that planetary atmospheres are complex, active chemical environments, producing molecules through a variety of pathways, some expected and some still not fully understood. The universe makes its chemistry in the dark, through pathways we are still quietly working to trace. Europa's surface is covered in a thin layer of radiation-processed material that gives it a slight reddish tint in some regions. The radiation from Jupiter's magnetosphere breaks apart molecules in the ice and creates new compounds, including hydrogen peroxide, sulfuric acid, and complex organic molecules, through a slow, continuous process called radiolysis. These compounds are then mixed into the ice by the constant tidal churning of the surface. Scientists think that some of this radiation-processed material, including the oxidants like hydrogen peroxide, may eventually be cycled down into the subsurface ocean, and if it is, it could serve as an energy source for potential life below, the same way oxygen in Earth's atmosphere supports life here. The radiation that makes Europa's surface so hostile to life may be, indirectly, one of the things that makes its hidden ocean hospitable. The very thing that makes a surface dangerous sometimes feeds the quiet life sheltering beneath it. The Great Red Spot produces an acoustic wave, a kind of sound, that propagates upward into Jupiter's stratosphere. Scientists discovered this recently, finding that the mechanical energy of the storm's rotation is transferred upward through the atmosphere as a gravity wave, an oscillation of the atmospheric layers driven by buoyancy. These waves deposit their energy in the stratosphere, heating it locally above the storm. This is one of the mechanisms thought to contribute to the puzzlingly high temperatures of Jupiter's upper atmosphere, far higher than simple solar heating would predict. The storm below powers the stratosphere above, sending acoustic and mechanical energy upward through the intervening layers. Jupiter's weather does not stay in its lane. It reaches up, silently, into the layers above it, shaping things at heights far removed from the churning, colorful clouds that are all we usually see. The influence of a storm travels farther than the storm itself. Even now, as you drift, the influence of distant things is traveling through layers you cannot see, shaping what is above. Jupiter has a very tenuous exosphere, a region above the main atmosphere where individual molecules escape into space, too sparse to behave as a gas, but too dense to be simply vacuum. In this thin region, hydrogen and helium leak slowly away from Jupiter, though at a rate so slow that the planet has lost a negligible fraction of its mass over its entire lifetime. The exosphere is also where some of the charged particles in Jupiter's radiation belts are born, energized by the planet's magnetic field and the input from Io's plasma torus. The boundary between atmosphere and space is not a sharp line. It is a gradual thinning, a slow transition from something to almost nothing, extending outward until the density drops below the point where any meaningful distinction between atmosphere and vacuum makes sense. Jupiter simply fades at its edges, like a watercolor painting, where the color thins to white at the margins, without any clear line where one thing ends and another begins. The most honest boundaries are the ones that fade gradually, without insisting on a clear edge. Jupiter emits more energy than it receives from the Sun. The ratio is approximately 1.6 to 1. For every unit of energy Jupiter absorbs from sunlight, it radiates about 1.6 units of energy back into space. The extra energy comes from the planet's interior, the slow gravitational contraction, and the residual heat of formation. This internal energy source makes Jupiter fundamentally different from Earth as a climate system. On Earth, the energy balance is almost entirely determined by sunlight. On Jupiter, a substantial fraction of the energy driving the weather comes from below. This is why Jupiter's equatorial and polar temperatures are more similar than Earth's. The internal heat is distributed more uniformly than solar heat, which falls primarily on the equatorial regions. Jupiter is a world with its own warmth, independent of any star, carrying the heat of its formation in its depths, like a long, slow memory of the violence that made it. A world that carries its own warmth does not need the light to be close in order to stay alive. The moon Callisto is in a state of almost perfect geological suspension. Its ancient, heavily cratered surface has barely changed in 4 billion years, because Callisto lacks the internal heat needed for volcanism or tectonic activity. It has no known mountains formed by geological processes, It has no evidence of resurfacing. Its craters have been modified slightly over time by the slow creep of ice under gravity, a process called viscous relaxation, where ice behaves over very long timescales like an extremely slow fluid, allowing the steepest crater walls to gradually flatten and the deepest floors to slowly rise. But even this is barely perceptible on human timescales. Callisto is, as much as any object in the solar system, a world at rest, a world that found its equilibrium billions of years ago and has been maintaining it ever since, drifting in its wide, slow orbit, changing only as slowly as time itself seems to move when you are very old and very still. Tonight, while you breathe slowly, a world that has not changed in 4 billion years drifts in its quiet, ancient orbit. Jupiter's role in the formation of the terrestrial planets is still debated among planetary scientists. One influential model suggests that Jupiter formed early and then migrated inward toward the Sun, disrupting the material in the inner solar system before being pushed back outward by Saturn's gravity. This inward then outward migration, called the Grand Tack hypothesis, would explain several features of the inner solar system, including the relatively small mass of Mars compared to Venus and Earth, and the particular composition of the asteroid belt. If this model is correct, Jupiter's early wandering shaped the raw material from which Earth was built, determining what kinds of rocks and ices were available, influencing the eventual composition of the oceans and atmosphere. Jupiter would then be not just a distant neighbor, but an architect, a world that wandered through the inner solar system billions of years ago and left its fingerprints on the ground beneath our feet. The world we stand on was shaped, quietly and indirectly, by something we can barely see in the night sky. Deep in Jupiter's metallic hydrogen layer, the pressure is so extreme that hydrogen atoms are stripped of their electrons, which then move freely through the material, like electrons in a metal. This is why it is called metallic hydrogen. It conducts electricity in the same way that metals like copper or iron do, even though it is composed entirely of hydrogen, the simplest element. This state of matter does not exist naturally anywhere on Earth, though it has been created briefly in laboratory experiments using extraordinarily powerful lasers and pressure apparatus. The currents of metallic hydrogen flowing in Jupiter's interior, driven by the heat from below and shaped by the planet's rapid rotation, generate Jupiter's magnetic field through a process called the dynamo effect, the same basic process that generates Earth's magnetic field, but running in a completely different material, under conditions that have no parallel anywhere in human experience. The same quiet principle that keeps a compass pointing north is running, deep inside Jupiter, in a material that does not exist on Earth. The mass of Jupiter is large enough that it subtly affects the motion of the Sun. Jupiter does not orbit the Sun in a perfectly fixed circle. Neither object is stationary. Instead, both the Sun and Jupiter orbit their common center of mass, called the barycenter of the Jupiter-Sun system. Because Jupiter's mass is about 1/1000th of the Sun's mass, this barycenter sits just slightly outside the physical surface of the Sun, roughly at 1 solar radius from the Sun's center. The Sun traces a small orbit around this point, wobbling slightly with a period equal to Jupiter's orbital period of 12 years. This wobble is how astronomers detect planets around distant stars. They look for the slight periodic motion of the star, the telltale wobble caused by a massive orbiting companion. Jupiter, in other words, is the reason we know how to find planets around other stars. Its own gravitational signature pointed the way. Every discovery carries within it the method for making the next one, quietly, in the structure of what we already know. The color of Jupiter's great red spot has changed over the decades of observation. In older photographs and drawings, the storm appears a deeper, more vivid red, sometimes described as brick red or salmon. In more recent images, it appears paler, more orange, sometimes nearly cream-colored in its central region. The cause of the red color itself remains debated among scientists. Some researchers believe it comes from complex organic molecules, tholins, created by ultraviolet radiation, reacting with the storm's unusual chemistry. Others suggest it comes from ammonium hydrosulfide or other sulfur compounds lifted to high altitudes by the storm. The fading color may be related to the storm's shrinkage or to changes in the depth from which the storm draws its material. We are watching a color that has been present in our sky, faintly visible through telescopes, for 3.5 centuries, and we still are not entirely certain what it is made of. Some things persist in plain sight for hundreds of years before revealing what they are made of. The interiors of giant planets like Jupiter are among the least explored regions of the solar system. We have sent probes to the surfaces of Mars and Venus and the Moon. We have landed on asteroids and a comet. We have touched the edge of the Sun's corona, but we have never been more than a few hundred kilometers into Jupiter's atmosphere, and the deep interior, the metallic hydrogen, the diffuse core, is known only through indirect inference, through gravity measurements and magnetic field observations, and the application of high-pressure physics developed in Earth laboratories. We know more about the surface of distant moons than we know about what lies 1,000 kilometers below Jupiter's cloud tops. The deep interior of Jupiter is the most inaccessible place in the solar system, not because of distance, but because of depth, because of pressure, because the planet itself is the obstacle. The closest unknown in the solar system is not at the edge of space. It is deep inside a world we have been watching for 400 years. Europa has a very thin atmosphere, composed almost entirely of oxygen, produced not by photosynthesis, as on Earth, but by the radiolysis of water ice on the surface. The same radiation-driven chemistry that processes the ice and creates the reddish staining. When radiation breaks apart water molecules in the ice, the hydrogen escapes into space more easily than the heavier oxygen, leaving behind a tenuous oxygen atmosphere. This atmosphere is so thin that it would be essentially undetectable without specialized instruments. The surface pressure is about 1 trillion times lower than Earth's atmospheric pressure at sea level. But the oxygen is there, quietly accumulating and escaping in a slow equilibrium, a ghost of an atmosphere around a frozen moon, produced by the same radiation that makes the surface hostile and potentially feeds the ocean below. The same source, the same energy, creating danger and atmosphere and the possibility of something alive, all at once. The universe is fond of situations where the same force creates both the obstacle and the opening. Jupiter has no solid surface, but it does have a weather layer, a region of the atmosphere where temperature and pressure allow cloud formation and the kind of atmospheric dynamics we associate with weather on Earth. This layer extends from roughly 50 kilometers above the 1 bar pressure level, the level where pressure equals Earth's atmospheric pressure at sea level, to roughly 50 kilometers below it. It is in this 100-kilometer band that all of the visible cloud activity takes place. The belts and zones, the Great Red Spot, the convective storms, the lightning, the ammonia crystals. Above the weather layer, the atmosphere thins into a clear stratosphere. Below it, the gas thickens too quickly for the kind of phase changes that produce clouds. Everything we have ever seen of Jupiter, every photograph, every painting, every image that has shaped our impression of the planet, comes from this thin, 100-kilometer shell wrapped around a world that extends tens of thousands of kilometers beneath it. What we see of vast things is always just the thin, lit surface of something far deeper. Jupiter's aurora is not a seasonal phenomenon. It runs continuously, powered by Io's constant volcanic output and by Jupiter's own rotation. On Earth, the northern lights are most vivid during periods of high solar activity, appearing a few times a year in high-latitude regions. On Jupiter, the aurora never stops. The polar regions of Jupiter glow continuously in ultraviolet light, in patterns that shift and pulse as the plasma torus and the magnetic field evolve, but that never fully extinguish. The Hubble Space Telescope has imaged Jupiter's aurora hundreds of times over the years, building up a library of observations that reveals how the aurora changes on timescales from minutes to years. In some images, the aurora forms a nearly complete ring around the pole. In others, it pulses and shifts in response to volcanic eruptions on Io. A world where the aurora never ends, where the light at the poles is always burning, quietly and continuously, in the cold dark of the outer solar system. There is something deeply restful about a light that burns continuously, without ever needing to be rekindled. The mass of Jupiter exerts a gravitational influence on Earth that is, over long timescales, significant. Jupiter's gravity contributes to the Milankovitch cycles, the slow, periodic variations in Earth's orbit and axial tilt that drive ice ages. Over periods of tens of thousands to hundreds of thousands of years, the gravitational tugs of Jupiter and the other outer planets cause Earth's orbital eccentricity to vary, its axial tilt to oscillate, and the orientation of its orbit to precess slowly. These variations change the distribution of sunlight across Earth's surface and through the year, driving the advance and retreat of ice sheets. The ice ages that shaped much of Earth's landscape and influenced human evolution were, at least in part, orchestrated by the gravity of a gas giant hundreds of millions of miles away. Jupiter has been shaping our climate on the longest timescales, patiently and indirectly, from its distant orbit, as it has been doing since before our species existed. The slow, ancient forces shaping the world are almost always invisible, and almost always vast, and almost always patient beyond our comprehension. The sodium cloud around Io is one of the strangest structures in the solar system. When ions and neutral atoms escape from Io's atmosphere, mainly sodium, some of them are not immediately swept into the plasma torus, but instead travel in longer, more complex paths through the Jovian system, forming an enormous diffuse cloud of sodium atoms that extends around Jupiter in a shape that does not follow any simple orbit. This cloud has been detected from Earth by observing the characteristic yellow light that sodium atoms emit when energized, the same yellow color produced by sodium street lamps here on Earth. Astronomers have photographed this cloud, pale, diffuse, enormous, surrounding Jupiter like an irregular halo, visible in specially filtered images. The same yellow light that illuminates our streets at night is also glowing, faintly, around Jupiter, emitted by atoms that were once part of a volcanic eruption on a moon of the largest planet in the solar system. The universe reuses its light. The light that illuminates a street and the light around a distant moon speak the same quiet language. Jupiter's axial tilt is so small, just 3 degrees, that it has almost no precession on human timescales. Earth's axis wobbles like a spinning top, completing one full precession in about 26,000 years. Jupiter's axis, barely tilted to begin with, precesses much more slowly, on a timescale of about 500,000 years for a full cycle. This stability is partly a function of Jupiter's enormous mass, which makes it resistant to gravitational perturbations from other bodies. Jupiter's orientation in space has been essentially the same for as long as complex life has existed on Earth. Its poles have pointed in the same direction. Its cloud bands have run in the same orientation. Its great red spot has sat in the same hemisphere for hundreds of millions of years. In a solar system full of wobbling, tilting, precessing worlds, Jupiter is the one that barely moves its head. Some things are so massive, so ancient, and so settled that the whole system moves around them while they remain still. The Juno spacecraft has survived far longer in Jupiter's intense radiation environment than its original design specifications required. It was designed for a primary mission of 37 orbits over roughly 20 months, but as of the mid-2020s, it had completed well over 60 orbits and continued operating. Each close pass through Jupiter's radiation belts deposits energy in Juno's electronics, slowly degrading them, a kind of aging, measured not in years, but in radiation dose. The mission team has been careful to manage Juno's exposure, adjusting its orbit and operations to extend its life as long as possible. Juno is, by now, an old spacecraft, weathered, radiation-worn, its instruments slightly degraded from their original calibration, and yet it keeps going, keeps sending data, keep making its close passes through the radiation and the magnetic environment, patient and persistent in the cold dark, doing the work it was sent to do. Even now, as you drift, a small spacecraft keeps its vigil around a giant world, patient and worn and still working. Jupiter's south pole, when imaged by Juno in visible light, reveals colors that are entirely unexpected. Deep blues and browns and whites, layered in complex cyclonic patterns, utterly unlike the orange and cream banding of the equatorial regions. The polar regions look, in some photographs, like satellite images of Earth's ocean floors, complex, swirling, enormous, ancient. Each of the cyclones surrounding the South Pole is approximately the size of the continental United States, and they have been arranged in their pentagonal pattern since Juno first photographed them. Why they maintain this configuration, why they do not merge or drift into chaos, is an active research question. Mathematical models of rotating fluids under the right conditions can produce these arrangements, but the details of why Jupiter's poles settled into pentagons and octagons rather than some other configuration is still not fully understood. The polar regions of Jupiter are a different world from the banded middle latitudes, darker, deeper colored, stranger, as though the planet kept a different face at its poles, turned away from the sun. The darkest, most ancient parts of things often reveal a face that the well-lit parts never show. Jupiter has been used as a gravitational slingshot by more spacecraft than any other planet. The technique, called a gravity assist or gravitational slingshot, uses the planet's orbital motion and gravity to accelerate a spacecraft and alter its direction without using any rocket fuel. A spacecraft approaching Jupiter from behind, in the same direction the planet is moving around the Sun, can effectively steal a tiny, imperceptible amount of Jupiter's orbital momentum, gaining speed while Jupiter loses an immeasurably small amount. The spacecraft flies past Jupiter faster than it arrived, heading in a new direction determined by the geometry of the encounter. Voyager 2 used Jupiter to reach Saturn. Cassini used Jupiter to reach Saturn more efficiently. New Horizons used Jupiter to reach Pluto. The exploration of the outer solar system has been, in large part, powered by Jupiter, a giant gravitational engine at the outer edge of the inner solar system, helping small machines, built by a small species, reach the distant corners of their planetary home. The largest things in a system do not always help through what they give, but through what they let pass, close enough to use them. The rings of Jupiter, thin and dark as they are, cast faint shadows on Jupiter's cloud tops during certain alignments of the Sun and the ring plane. These shadows are extremely faint, detectable only in carefully processed images, but they are there, the shadow of a nearly invisible ring falling on the clouds of an enormous planet. When Juno was in the right position and geometry, scientists were able to image these shadows and use them to refine measurements of the ring structure. The shadow of a dark ring on a cloudy planet, cast by a sun 5 times more distant than the one that lights our day, observed by a spacecraft, making its fast, close pass through a radiation environment that slowly wears away its instruments. There is a whole story in that image, a quiet story of patience and distance, and the delicate persistence of the faint things that surround vast ones. The faint things that circle the vast ones leave their marks in ways that require patience to see. Jupiter's moons are tidally distorted by the planet's gravity. Because Jupiter's gravity is stronger on the side of each moon facing the planet than on the far side, it pulls the near side more strongly, stretching the moon very slightly into an elongated shape, like a ball of clay pulled gently from both ends. This tidal distortion is tiny for the outer moons and larger for the inner ones. And for Io, which is closest to Jupiter, it is responsible for the tremendous tidal heating that drives all that volcanic activity. The same principle, tidal distortion, operates on Earth, causing the oceans to bulge toward and away from the moon, producing the tides that rise and fall along every coastline every day. The ocean outside your window, if you are near one, rises and falls because the moon pulls on it, very slightly, from its quiet distance. And Io's interior stays molten for the same reason, scaled up by the mass of Jupiter and the closeness of the orbit. The same gentle principle, applied at different scales, producing the tides of Earth and the fires of Io. The same quiet force that moves the sea below your window melts the rock inside a moon 400 million miles away. Jupiter has been the subject of human observation for at least 2,000 years. Babylonian astronomers in the 7th and 8th centuries BCE tracked Jupiter across the sky, recording its position relative to the fixed stars on clay tablets. They developed mathematical methods for predicting its future positions, systems of arithmetic that could calculate where Jupiter would be weeks or months in advance, without any understanding of orbital mechanics, simply by finding the patterns in years of careful observation. These Babylonian records are among the oldest surviving astronomical documents, and they are remarkably accurate. Jupiter's positions calculated from ancient clay tablets match modern calculations within the expected margins of ancient measurement. The planet that Juno is orbiting today is the same one that Babylonian astronomers tracked by eye from rooftops thousands of years ago, recording it on clay, calculating its path through the sky, finding its patterns with nothing but patience and time. The same ancient light fell on ancient eyes and on your window tonight, patient and unchanged across all the years between. Jupiter's diameter is about 11 times the diameter of Earth. If Earth were the size of a grape, Jupiter would be the size of a basketball. If you could drive a car at highway speeds around Jupiter's equator, the journey would take more than 400 days without stopping. If you lined up all the planets in the solar system side by side, Jupiter would be wider than all the others combined, with room left over. These comparisons are standard ways of communicating Jupiter's size, and they do their job. They make the scale real, at least briefly, before the mind softens the numbers, and they return to abstraction. What the numbers cannot quite capture is the feeling that comes with truly sitting with Jupiter's scale. The slow, quiet vertigo of realizing that the largest thing you can easily imagine is dwarfed by something that is itself a small planet, in a small solar system, in an ordinary galaxy, in a universe of 2 trillion galaxies. Rest in that for a moment. Let yourself be small. Smallness, at the right scale, feels like peace. Jupiter's atmosphere is mostly hydrogen and helium, the 2 simplest elements in the universe, the ones that formed first, in the first few minutes after the Big Bang. The hydrogen and helium in Jupiter's clouds have been there since the early solar system, and before that they were in the solar nebula, and before that in the interstellar medium, the diffuse gas between stars, and before that in older stars that formed and lived and died billions of years before our sun existed. The hydrogen atom in a water ice crystal in Europa's ocean was forged in the Big Bang itself, 13.8 billion years ago. It has been a hydrogen atom ever since, inside stars, in the interstellar medium, in the early solar nebula, in the water ice of a forming moon, in the ocean beneath the ice, waiting for something to notice it. That hydrogen atom is older than our solar system. It is one of the oldest things that exists. The ancient, slow, patient things were here before everything else, and they will be here after. Jupiter's gravity keeps the solar system organized. Without its mass, the asteroid belt would be more chaotic. Comets would wander more freely through the inner solar system, and the orbits of the other planets would be perturbed more easily by random close encounters over geological timescales. Jupiter is the gravitational anchor of the outer solar system, not a wall or a net that actively stops things, but a massive, constant presence whose gravity shapes the paths of everything in its neighborhood, nudging, redirecting, capturing, and releasing material on timescales too long for any human lifetime to encompass. It has been doing this for 4.5 billion years. The same slow gravitational work, day after day, orbit after orbit, patient and enormous, shaping the neighborhood it has always lived in, without knowing it is doing so. The largest presences in any system do their most important work silently, simply by being there. The clouds of Jupiter are never still. Even in regions that look calm in a single photograph, the cloud bands are moving at hundreds of miles per hour relative to each other, the boundaries between them constantly generating eddies and swirls and small vortices. Time-lapse videos assembled from multiple Voyager images in 1979 showed, for the first time, the extraordinary dynamism of Jupiter's weather, the cloud bands flowing in opposite directions, small storms forming and dissipating, the great red spot surrounded by a complex, swirling collar of smaller vortices. Jupiter has no moment of stillness. It has been turning and churning and swirling continuously for over 4 billion years. Every image we have of Jupiter is a single frozen moment in an unbroken flow of motion that began before the first bacteria appeared on Earth and has continued without interruption through every chapter of life's history on our small, still world. Tonight, while you breathe slowly, a world that has never been still for a single moment turns in the patient dark. Jupiter may eventually lose its great red spot entirely. Scientists who track the storm's dimensions have noted that it is shrinking at a rate that, if continued linearly, would see it disappear within decades, though the rate of shrinkage varies and may slow or reverse. What would Jupiter look like without the great red spot? The storm has been a feature of the planet for as long as we have been looking carefully, and it has become so central to Jupiter's visual identity that imagining Jupiter without it requires a small act of imagination, like imagining a familiar face without a feature that has always been there. Jupiter would still have storms. It would still have belts and zones. It would still be the largest planet in the solar system, 4.5 billion years old, circling the sun with the same patient constancy. But it would look different, and something ancient and familiar would be gone. The universe does not keep its beautiful things forever. It simply keeps them for a very long time. The most ancient things eventually grow still, and the universe, gently, continues around their absence. Jupiter is not a failed star. That description, while evocative, implies that Jupiter was trying to become something it was not, that it fell short of a goal. A better way to think of it is that Jupiter is exactly what the physics of its situation made it, the largest possible planet, formed from the right materials, in the right place, at the right time, too massive to be a rocky world and too small to be a star, occupying its own specific category of object, with its own specific character. It is a gas giant, a category of world that turns out to be common in the galaxy, that forms around many stars and plays a similar organizing role to the one Jupiter plays in our solar system. Jupiter is not a lesser thing. It is precisely the thing it is, enormous and ancient and full of storms and moons and mystery, doing exactly what a gas giant 4.5 billion years old does, circling quietly in the cold outer dark, patient as it has always been. It is enough to be exactly what you are, ancient and patient, and quietly turning in the dark. Jupiter, seen through a small telescope on a clear night, is a tiny pale disk with faint brownish stripes. You can see it yourself, with almost any telescope, from almost any dark place on Earth. On the right night, you can see the 4 Galilean moons as tiny points of light on either side of the planet, just as Galileo saw them 400 years ago from a cold rooftop in Padua with a telescope he had built himself. There is something extraordinary about that accessibility. This enormous, ancient, storm-wrapped world that we have sent spacecraft to, that we have studied with instruments of breathtaking sophistication, that has shaped the history of our solar system and the evolution of life on Earth. It is also just there, on a clear night, visible to the naked eye as a steady bright point, available to anyone who steps outside and looks up and knows roughly where to look. The universe does not hide its largest planet. It just hangs it in the sky, quietly, and waits. Even now, as you drift, the largest planet in the solar system is hanging in the dark above the roof of your house, patient and bright, waiting for anyone willing to look up. Close your eyes now. The iron in your blood was forged in the heart of a dying star. Not this star, not our sun, which is still in the middle of its quiet life, fusing hydrogen into helium in its core. An older star, one that lived and burned and eventually collapsed and exploded billions of years before our solar system formed. In that explosion, in the tremendous heat and pressure of a dying star's final moments, heavy elements were forged: iron and calcium and the oxygen in your lungs and the carbon in every cell of your body. That material was scattered into space, drifting for millions of years in the cold interstellar dark, until gravity gathered it into the disk that formed our solar system, and some of it became the Earth, and some of the Earth became the ocean, and some of the ocean became life, and some of that life became you, lying here in the dark, breathing slowly, with iron in your blood that is older than the ground beneath your feet. You are not separate from the universe you have been listening to tonight. You are made of it. You are a temporary arrangement of ancient atoms, resting for a few hours on a small, warm world, in the outer arm of an ordinary galaxy, in a universe so vast and so old that scale becomes meaningless and only the quiet remains. Jupiter is out there tonight, vast and patient and still turning. Its moons are tracing their ancient orbits, Io burning, Europa dreaming beneath its ice, Ganymede carrying its hidden ocean, Callisto wearing its ancient scars in silence. The great red spot is turning slowly, as it has turned for centuries, in the southern cloud bands of a world that does not know we are watching it. And you are here, breathing, resting, your body doing what it has always known how to do, letting go, growing heavy, allowing sleep to come. The universe is 4.5 billion years older than you. It has been patient for a very long time. It can be patient a little longer while you rest. Let your breathing slow. Let the thoughts grow faint. Let the enormous, quiet dark of space settle around the edges of your mind like a cool and ancient blanket. You have nothing to do tonight, nowhere to be, nothing to solve. You are still, and the universe is turning slowly around you, doing what it does, as it has always done. I hope you sleep well tonight and dream softly. Good night. The wind speeds inside Jupiter's equatorial jet streams are among the fastest sustained winds measured anywhere in the solar system. Near the equator, cloud features move at speeds of up to 540 kilometers per hour, faster than the most powerful hurricanes ever recorded on Earth, sustained not for hours or days, but continuously, without pause, year after year, century after century. These jet streams are not driven by temperature differences between the equator and the poles the way Earth's jet streams are. They appear to be driven instead by deep internal processes, convection in the interior, the heat rising from below, interacting with the planet's rapid rotation. They may extend deep into the planet, far below the visible cloud tops, running like invisible rivers of wind through the dense, dark layers beneath. No one has ever flown through them. No instrument has ever been inside them long enough to fully characterize them. They simply run, as they have always run, patient and enormous and invisible from the outside. Some of the most powerful things in the universe run continuously, without anyone watching, without anyone needing to know. Jupiter's moons cast shadows on Jupiter's cloud tops that are visible through Earth-based telescopes. When Io, or Europa, or Ganymede passes directly between Jupiter and the Sun, a small, dark circular shadow falls on Jupiter's upper atmosphere, a tiny black dot moving slowly across the face of the planet. Amateur astronomers routinely observe and photograph these shadow transits, and they happen frequently, since the Galilean moons orbit quickly and the geometry aligns often. There is something quietly wonderful about that. Standing in a backyard with a modest telescope on a clear night, watching the shadow of a moon 400 million miles away move slowly across the face of a gas giant, the same event that Euler Roemer used 350 years ago to measure the speed of light. The universe keeps offering the same observations to anyone patient enough to look. The same quiet event that revealed the speed of light is still happening tonight, for anyone willing to step outside and look up. Jupiter's magnetosphere contains a region called the magnetodisk, a flattened disk of plasma that extends outward from Jupiter's equatorial plane, stretching tens of millions of kilometers into space. This magnetodisk forms because Jupiter's rapid rotation flings the plasma trapped in its magnetic field outward toward the equator, flattening the otherwise roughly spherical inner magnetosphere into a disk shape. The magnetodisk is one of the largest discrete structures in the solar system, a vast, invisible, rotating pancake of hot plasma surrounding Jupiter, threaded by magnetic field lines, pulsing with the energy fed into it by Io's volcanic output. Spacecraft passing through the magnetodisk experience dramatically increased radiation and particle fluxes. The magnetodisk rotates with Jupiter, sweeping through space with the planet's 10-hour rotation period, an enormous invisible wheel turning in the dark around the largest planet in the solar system. The invisible things that surround vast objects are often larger than the objects themselves, turning quietly in the dark. The water in Jupiter's atmosphere was partially mapped by the Juno spacecraft's microwave radiometer, which can detect the thermal emission of water vapor at different depths. The measurements revealed that Jupiter's water abundance varies significantly with latitude. Some regions are much drier than others, and the equatorial zone appears to have a higher water content than the temperate latitudes. Understanding Jupiter's water is important because water ice was the boundary material in the early solar system. The snow line, beyond which water ice could form solid particles, was a critical dividing line in the formation of rocky versus gaseous planets. Jupiter formed just beyond this line, and the water it contains is a record of conditions in the early solar nebula at the distance where Jupiter formed. Every measurement of water in Jupiter's atmosphere is a piece of the story of how the solar system assembled itself from dust and ice and gas 4.5 billion years ago, in a process too slow and too vast for any mind to hold all at once. Quietly, the water inside a distant giant carries the memory of the solar system's first cold morning. The orbital period of Jupiter's moon Ganymede, just over 7 Earth days, is exactly twice the orbital period of Europa and exactly 4 times the orbital period of Io. This Laplace resonance is so precise that the 3 moons can never all be at the same orbital longitude simultaneously. Their geometry is constrained by the resonance in a way that prevents certain configurations from ever occurring. The resonance also means that every time Io completes 4 orbits, there has been exactly 1 conjunction between all 3 moons, a moment when Io, Europa, and Ganymede are aligned on the same side of Jupiter. These conjunctions happen regularly, like a slow, precise clock, ticking once every 42.5 hours, in the cold dark of the outer solar system, driven by nothing but gravity and the momentum of 4.5 billion years of continuous orbital motion. Some clocks run without hands or faces, ticking in the dark, keeping time for no one in particular. Jupiter's interior rotation, the deep layers below the weather zone, rotates as a nearly rigid body, with most of the interior completing 1 rotation in about 9 hours and 55 minutes regardless of latitude. This is called the System 3 rotation period, and it is measured by tracking the rotation of Jupiter's magnetic field, which is anchored in the deep interior. The difference between this deep rotation rate and the faster-moving equatorial cloud tops amounts to roughly 5 minutes, meaning the clouds at Jupiter's equator are outrunning the deep interior by about 5 minutes per rotation. Over the course of a Jovian day, the equatorial clouds drift several degrees ahead of the internal rotation. Over years, This differential adds up to many full laps. The surface of Jupiter is in constant, slow motion relative to its own interior, sliding forward, always, in a drift that has been going on since Jupiter first formed and found its spin. The surface moves quietly ahead of the deep, always slightly ahead, never stopping, never catching up. Jupiter has a faint glow visible in infrared wavelengths even on its night side. Because Jupiter generates its own heat and radiates it outward, the night side of Jupiter, the hemisphere turned away from the sun, still glows in infrared, warmer than the surrounding space. Infrared telescopes observing Jupiter can see both hemispheres glowing, the day side brighter with reflected sunlight, and the night side dimmer, but still warm with its own internal heat. This is one of the clearest observational signatures of Jupiter's internal energy source, the fact that its night side is not cold and dark, but gently warm, radiating the slow, ancient heat of formation. The warmest regions on Jupiter's night side are associated with the deep cyclonic storm systems and with regions of atmospheric upwelling, where warm gas from below rises close enough to the surface to radiate its heat outward into space. Even now, as you drift, a world on the far side of its sun glows gently from its own ancient warmth. The surface of Io changes measurably between spacecraft visits. When Voyager 1 flew past Io in March of 1979, it photographed a world covered in volcanic features. When Voyager 2 flew past, just 4 months later, some of those features had changed. New lava flows had appeared. Some volcanic vents had grown or shifted. When Galileo began orbiting the Jovian system in 1995, the changes were even more dramatic. Large regions of Io's surface had been resurfaced entirely by lava flows in the intervening 16 years. Io is the only body in the solar system, other than Earth, where we have been able to directly observe significant geological change between visits. It is a world that does not stand still long enough to be fully mapped before the map becomes outdated. In the time it takes to plan and launch and fly a spacecraft to Jupiter, Io will have repainted significant portions of its surface in fresh lava. The most restless things leave no permanent record. They simply begin again, quietly, over and over. Jupiter's atmosphere contains molecular nitrogen, argon, krypton, and xenon, noble gases that provide clues about where Jupiter formed. Noble gases do not react chemically with other elements, which means their abundances in Jupiter's atmosphere reflect the conditions of the material Jupiter accreted, rather than any subsequent chemistry. The Galileo probe measured these noble gas abundances in 1995 and found that argon, krypton, and xenon were all more abundant in Jupiter than in the Sun, which was surprising because these heavy noble gases are only incorporated into solid ice at very low temperatures, far colder than the temperature at Jupiter's current location. The finding suggests that some of Jupiter's material, or the planetesimal seeds that first formed and then swept up the surrounding gas, originated in the very cold outer reaches of the protosolar nebula, far beyond where Jupiter currently orbits. Jupiter may have gathered material from the cold edge of the early solar system, carrying it inward as it grew. The things that traveled farthest to reach us are often the ones that carry the oldest, coldest memories. Ganymede's ocean is estimated to contain more liquid water than all of Earth's surface oceans combined. The total volume of water in Ganymede's subsurface ocean, held between layers of ice and rock under enormous pressure, dwarfs the Pacific and Atlantic and all the other oceans of our world taken together. If that water could somehow be brought to the surface and spread across Ganymede's face, it would create a global ocean hundreds of kilometers deep. The sheer volume of water hidden beneath the icy crust of a moon, 400 million miles from Earth, suggests something about the distribution of water in the solar system that we are still processing. That our planet, with its blue surface and its liquid oceans, is not the exception, but rather a visible instance of something the solar system does quietly and extensively holding water in cold and dark and hidden forms throughout the outer system, patient and vast, and mostly invisible to us. Tonight, while you breathe slowly, a hidden ocean larger than all of Earth's seas rests in the quiet dark, beneath the ice of a distant moon. The aurora on Ganymede pulses in a rhythm, driven by Jupiter's magnetic field. As Jupiter rotates, and its magnetic field sweeps past Ganymede, the interaction between the two magnetic environments changes, and Ganymede's aurora shifts and brightens, and dims in response. Scientists measured this pulsation using the Hubble Space Telescope, and used the pattern of the pulsations to infer the presence of the subsurface ocean, because the ocean's salty water conducting electricity dampened the expected pulsations, producing a pattern that matched what you would predict if a conducting layer existed between the surface and the rocky interior. The discovery of an ocean hidden beneath another world's ice, inferred from the flickering of an aurora observed by a telescope in Earth orbit, is one of the most indirect and elegant pieces of scientific detective work ever accomplished. The universe left a clue in a light show, and someone patient enough to measure the timing found it. The universe hides its oceans beneath ice, and reveals them in the rhythm of lights too faint to see with the naked eye. Jupiter's inner magnetosphere is shaped partly by a phenomenon called corotation, the tendency of the plasma trapped in Jupiter's magnetic field to rotate with the planet at the same rate. Near Jupiter, the magnetic field is strong enough to force the plasma to chorotate, to spin with Jupiter's 10-hour period. Farther out, the plasma cannot keep up with the rotating field, and it lags behind, stretching and distorting the outer magnetosphere. The boundary between the chorotating inner magnetosphere and the lag region in the outer magnetosphere is a region of intense electromagnetic activity, where energy is dissipated and radio waves are generated. This region powers some of the radio emissions from Jupiter that can be detected on Earth. It is also where some of the most energetic charged particles in Jupiter's radiation belts are produced. Electrons and ions accelerated to near relativistic speeds by the electromagnetic activity at the corotation boundary, in a region of space that has no analog anywhere in the inner solar system. The places where one thing cannot quite keep up with another are always the most energetic, the most turbulent, the most alive. The thin oxygen atmosphere of Europa is constantly being replenished, because the radiation environment continuously strips oxygen from the surface ice. The atmosphere would fade away within a few years if it were not constantly being remade. Every moment, radiation from Jupiter's magnetosphere is breaking water molecules in the surface ice, the lighter hydrogen escaping and the heavier oxygen accumulating. And every moment, some of that oxygen is being stripped away by the solar wind and by Jupiter's magnetic field. The atmosphere exists in a dynamic equilibrium, always being destroyed, always being remade, never the same collection of molecules from one year to the next, but always the same thin, ghostly presence above the ice. It is a kind of atmosphere that lives only because it is constantly dying and being reborn, a cycle driven by the radiation of a world it orbits and the physics of a molecule it is made of. Some things persist not by remaining unchanged, but by being continuously, quietly renewed. Jupiter's cloud bands are separated by jet streams that move in alternating directions. The light zones are high-pressure regions where gas is rising, and the dark belts are low-pressure regions where gas is descending. Between them, the jet streams run east or west, eastward in some latitudes, westward in adjacent ones, creating a pattern of alternating wind directions that covers the planet from roughly 45 degrees north to 45 degrees south latitude. Beyond those latitudes, the jet stream pattern breaks down, and the polar cyclonic regions take over, with their different dynamics. The jet stream boundaries are where Jupiter's most complex and turbulent weather occurs, where the edge of a belt meets the edge of a zone, where eastward and westward winds shear against each other, producing the swirls and vortices and small storm systems that give Jupiter its intricate, layered appearance in detailed images. Every swirl you see in a photograph of Jupiter is a story of two winds moving in opposite directions, rubbing against each other, producing something beautiful at their boundary. Beauty, in weather as in most things, tends to arise at the boundaries between opposites. The Pioneer spacecraft that first visited Jupiter in the 1970s carried gold anodized aluminum plaques depicting a man and a woman, the location of our solar system in the galaxy, and basic information about our species. These plaques were not intended as messages to Jupiter. They were intended for any intelligent life that might intercept the spacecraft after it left the solar system. Pioneer 10, which flew past Jupiter in 1973, is now far beyond the outer edge of the solar system, still traveling, still carrying its plaque, though its power source has long since faded, and it can no longer communicate with Earth. Somewhere out there, in the cold dark between the stars, a small machine built by human hands is drifting with a picture of a human man and woman engraved on metal, sent outward from the solar system by Jupiter's gravity, carrying a quiet message into the vast silence that no one may ever find. We sent our picture into the dark, carried by Jupiter's gravity, in the hope that somewhere in the patient silence, something might one day find it. The temperature at Jupiter's 1 bar level, the pressure level equivalent to Earth's atmospheric pressure at sea level, is approximately minus 110 degrees Celsius. This is the reference altitude from which planetary scientists measure Jupiter's atmospheric structure, the 0 point, in a sense, from which depths and heights in the atmosphere are reckoned. Above this level, the atmosphere thins and cools further into the stratosphere. Below it, temperature and pressure increase together as you descend into the lower troposphere, the water cloud deck, and eventually the deep, hot interior. The 1 bar level sits in the middle of Jupiter's ammonia cloud layer, in the cold, dim, pale orange clouds that give Jupiter its characteristic color in photographs. It is a place of slow, horizontal cloud motion and gentle vertical mixing, a relatively calm layer in a planet that is anything but calm at most other depths. A still band in a churning world, drifting in its pale orange quiet. Even in the most turbulent systems, there is always one layer that moves more slowly than the rest, resting in its particular cold. Jupiter has a faint magnetic north and south pole, but unlike Earth's magnetic poles, they are not particularly close to the rotational poles. Jupiter's magnetic field is complex, not a simple dipole aligned roughly with the rotation axis the way Earth's is, but a more irregular, multipolar structure. Juno's detailed magnetic mapping has revealed that Jupiter's magnetic field has significant regional variations, including a region near the equator in the northern hemisphere, where the field is unusually strong, a kind of magnetic anomaly with no clear Earth analog. This irregular field structure suggests that the dynamo generating it, the flowing metallic hydrogen in Jupiter's interior, has a more complex geometry than Earth's molten iron outer core. Jupiter's interior flows are not uniform or symmetric. They are shaped by the same differential rotation that shapes the atmosphere above, producing a magnetic field that is not a simple shape, but a complex, irregular, ancient pattern, turning with the planet in the deep dark below the clouds. The deepest things are never the simplest things. Jupiter's rings, though dark and faint, were observed to have changed slightly between the Voyager era and more recent observations. The rings appear slightly different in structure. Some components have faded, others have changed in brightness. These changes are consistent with the ongoing loss of dust from the ring system, as particles slowly spiral inward under the influence of Jupiter's magnetic field, and with new inputs from meteor impacts on the source moons. The rings of Jupiter are not static structures. They are dynamic, slowly evolving, continuously losing and gaining material, running an energy budget that depends on a steady stream of impacts on 4 small inner moons. In 100 million years, if the impact rate on the source moons declines significantly, Jupiter's rings could fade entirely. In a different 100 million years, a new moon could drift inside the Roche limit and be torn apart into a new ring system, bright or faint, or somewhere between. The universe does not keep the same decorations forever. It refreshes them, quietly, on timescales we are not patient enough to watch. The word Jupiter comes from the Latin Jupiter, derived from the Proto-Indo-European root meaning sky father, the same linguistic root that gives us the Greek god Zeus, the Hindu Deus Pita, and the concept of the divine sky in many ancient cultures. The planet was named for the king of the Roman gods because it is the largest and brightest of the outer planets, moving slowly and regally through the zodiac, outshining everything except the sun, moon, and Venus. Many cultures across history independently assigned their most powerful sky deity to this particular point of light, not knowing it was a gas giant, not knowing it had moons or storms or a magnetic field, but sensing from its brightness and its slow, steady motion that it was something of consequence. They were not wrong. Jupiter is, in every measurable sense, the most consequential planet in our solar system, the one that shaped everything else, that protected and endangered and organized and defined the neighborhood we live in. Ancient people named it for their king of the gods without knowing why, and it turns out they were not far wrong. Jupiter's magnetic equator is not perfectly aligned with its geographic equator, because Jupiter's magnetic dipole is tilted about 10 degrees relative to its rotation axis. The magnetic equator sweeps north and south as Jupiter rotates, moving like a slow wave through the Jovian system. This wobble drives the pulsations in the Io plasma torus, the variations in the radiation belts, and the rhythmic changes in the aurora. It is what gives Jupiter's radio emissions their periodic structure. The radio bursts come and go as the magnetic equator sweeps past the source regions, producing a natural radio pulse with a period equal to Jupiter's rotation. This pulsing was how astronomers first measured Jupiter's interior rotation period in the 1950s, before any spacecraft had visited the planet. A 10-degree tilt, a sweeping magnetic equator, a radio pulse, and from that, the rotation rate of the deep interior of a gas giant. The universe offers clues in its rhythms to anyone listening carefully enough. Even now, as you drift, Jupiter's magnetic wave sweeps through the system, pulsing its ancient radio signal into the quiet dark. The surface of Europa has very few impact craters compared to what you would expect for a body its size and age. Models of the impact rate in the outer solar system predict that Europa should have accumulated thousands of craters over its 4-billion-year history. Instead, it has fewer than 30 recognized impact structures. The explanation is the same one that explains the young surface age. The ice shell is continuously being overturned and renewed by tidal processes, erasing old craters before they can accumulate. The few craters that do exist on Europa are themselves unusual. Many of them are flat or have raised centers, because the ice relaxes and flows slowly over time, softening the sharp features that a fresh impact would produce. Even Europa's craters are being slowly erased, filled in, healed by the patient movement of the ice. A world that heals its own scars, over and over, in the cold quiet beneath a sky dominated by the enormous disk of Jupiter. A world that keeps erasing its own scars, and beginning again, quietly, does not carry its wounds forever. Jupiter has been observed to occasionally absorb small comets and asteroids without producing visible impact scars. The comet Shoemaker-Levy 9, in 1994, produced scars visible for months, but smaller objects, tens of meters to a few kilometers in size, impact Jupiter regularly and leave no detectable mark, absorbed into the vast atmosphere without disturbing the cloud structure. And in 2009, an impact scar similar in size to the Shoemaker-Levy impacts was discovered by an amateur astronomer, a dark bruise in the cloud tops that persisted for weeks. In 2010, observers detected brief flashes, fireballs, from impacts too small to leave lasting marks. Jupiter is being impacted regularly, quietly, absorbing the debris of the solar system in its vast atmosphere, processing it, incorporating it, moving on. Each impact is erased within days or weeks by the slow churning of the clouds, and the planet continues its patient orbit, unmarked. The vast things absorb what comes and keep moving, carrying no visible record of the countless small things they have taken in. Jupiter's day, at just under 10 hours, means that a point on Jupiter's equator moves at roughly 45,000 kilometers per hour, relative to the planet's center of rotation. By comparison, a point on Earth's equator moves at about 1,600 kilometers per hour due to Earth's rotation. Jupiter spins nearly 30 times faster than Earth at the equator, and because Jupiter is also 11 times wider, the actual speed of the equatorial surface is more than 50 times faster than Earth's. This extreme rotation rate has shaped Jupiter's oblateness, its flattening at the poles, and drives the entire meteorological system. Without this rapid spin, the cloud bands would not exist. The belts and zones, the jet streams, the organized structure of Jupiter's weather, all of it emerges from the interaction between the internal heat rising from below and the fast rotation imposing a preferred direction on the fluid dynamics. Take away the spin, and Jupiter's atmosphere would be a featureless, slowly convecting sphere of gas. The spin is what gives it its face. Speed, applied with patience and consistency over billions of years, builds the most beautiful structures. The radio emissions from Jupiter were first detected accidentally in 1955 by astronomers Bernard Burke and Kenneth Franklin, who were conducting a survey of radio sources in the sky and noticed a periodic, strong radio signal they could not immediately explain. They eventually traced it to Jupiter, a discovery that was entirely unexpected, since no one had predicted that a planet could produce such powerful radio emissions. The signal turned out to be the decametric radio emission produced by the interaction of Io's plasma with Jupiter's magnetic field, a phenomenon that was not fully understood until decades later. The discovery opened a new chapter in planetary science, establishing that planets could be powerful radio emitters, and eventually leading to the search for radio emissions from exoplanets as a way to detect their magnetic fields. A survey accidentally picked up a signal from the largest planet, and the ripples of that accidental discovery are still spreading through planetary science today. The most important findings often arrive when you are looking for something else entirely, in the patient work of simply paying attention. Europa Clipper, launched in October 2024, is the largest planetary science spacecraft NASA has ever built. It carries 9 scientific instruments designed to study Europa's ice shell, ocean, and surface chemistry during approximately 50 close flybys over 4 years. It is not designed to land or drill. It will fly past Europa repeatedly, each time collecting data and building up a picture of the moon's structure and habitability. The spacecraft used a gravity assist from Mars and then from Earth to gain the speed needed to reach Jupiter, arriving in the Jovian system in the early 2030s. It will then spend years in orbit around Jupiter, making carefully planned close passes of Europa, each one adding data points to a picture that scientists have been assembling since Galileo first observed the Galilean moons in 1610. 400 years of watching from a distance, and now a spacecraft close enough to smell the ice, if ice had a smell, gathering the patient details of a world that may not be alone. The universe keeps its patient ones. The ones who watch long enough eventually get to go closer. Jupiter's helium abundance is slightly lower than the Sun's. In the outer solar system, where conditions were cold enough and Jupiter's gravity strong enough to retain almost everything, you would expect Jupiter's composition to closely match the Sun's, and in most respects it does. The hydrogen to helium ratio should be roughly solar. But measurements show that Jupiter has slightly less helium in its outer atmosphere than the Sun. The explanation is that helium, under the pressure conditions in Jupiter's deep interior, gradually separates from the hydrogen. It becomes slightly immiscible, like oil in water at the right conditions. The helium forms droplets that rain downward through the metallic hydrogen layer, settling toward the deeper interior. This helium rain is happening right now, deep inside Jupiter, tiny droplets of liquid helium falling slowly through the metallic hydrogen, releasing gravitational energy as they fall, contributing to Jupiter's internal heat. It is one of the most exotic processes in the solar system, happening invisibly, in the deep dark, without any witness. Quietly, in the deep dark of the largest planet, it rains helium, and no one is there to hear it fall. Jupiter's north equatorial belt, one of the most consistent and prominent dark bands on the planet, contains a feature called a hotspot. These are regions of unusually low cloud cover that allow deeper, warmer layers of the atmosphere to be seen, making them appear darker and warmer in infrared observations. The Galileo probe descended into one of these hotspots in 1995, which is why it detected less water than expected. The hotspots are the driest, clearest windows into Jupiter's atmosphere, and they are not representative of the planet as a whole. Hotspots form in the downwelling regions of large atmospheric waves called Rossby waves, the same class of planetary waves that influence Earth's weather patterns at mid-latitudes. These waves on Jupiter are enormous. A single Rossby wave on Jupiter can span a distance greater than the diameter of Earth. The same kind of atmospheric wave that nudges a cold front across a continent is operating, at planetary scale, in the bands of a gas giant 400 million miles away. The same quiet wave that bends the weather above your house bends the clouds of a giant world in the distant dark. Jupiter's gravitational field is not perfectly smooth. It has small variations called gravitational harmonics that reflect the distribution of mass inside the planet. As Juno flies past Jupiter on each close approach, its orbit is perturbed by these gravitational variations, and by measuring the perturbations with extraordinary precision, tracking the Doppler shift of Juno's radio signal from Earth to a fraction of a millimeter per second, scientists can infer the internal mass distribution that produced them. This technique, called gravity science, has revealed that Jupiter's interior is not uniformly distributed, that the weather zone dynamics extend far deeper than the clouds suggest, and that the core is diffuse and extended. The entire knowledge of Jupiter's deep interior, the metallic hydrogen, the fuzzy core, the deep rotation, comes from measuring tiny wobbles in the path of a spacecraft the size of a basketball court, flying fast through a radiation field that is slowly destroying its electronics. Some of the deepest knowledge comes from the most delicate measurements, a fraction of a millimeter per second, carrying the secret of a planet's interior. Jupiter's equatorial plane is nearly aligned with the plane of the solar system. Its axial tilt of just 3 degrees means it orbits the Sun with its equator almost exactly in the plane of the ecliptic, the plane in which all the planets orbit. This is thought to reflect Jupiter's formation in the protoplanetary disk. A massive body that forms from a disk tends to have its equatorial plane aligned with the disk. The slight 3-degree tilt may have been induced by gravitational interactions with the other giant planets in the early solar system, a small but permanent nudge from the long-ago gravitational dance between Jupiter and Saturn. Saturn's influence on Jupiter has been subtle and ancient and small in its result. 3 degrees of tilt, maintained for 4.5 billion years. But it is there, a record of the gravitational conversation between 2 giant worlds in the formative years of the solar system, still written in the orientation of Jupiter's clouds as they turn in the cold outer dark. Even the smallest tilts carry the memory of ancient forces, preserved in the orientation of a turning world. The rest here for a moment. The dark is wide and patient, and there is more quiet still to come.